request Professor Pandey to chair the session.
Okay, thank you. Thank you. Thank you. Good. Navarran, you're ready?
Yes.
Very good. So, good morning to all of you again. This is the session on star formation and star clusters. You all know. The beauty is, on which we'll talk about, is 4K by 4K CCD. See how things have moved forward when we started using that too quite late in 1991. We used 385 by 576 CCD. Now it doesn't exist. I have tried to verify. Right now we have 4K by 4K, even many more. If you don't have, make a mosaic of such CCDs. Right, because clusters require large field of view. So that can be done only when you have a large format CCD camera or mosaic of several CCDs. So I'm happy that Ramakant Yadav will give an overview of 4K by 4K CCD measure, what are its capabilities, and how it has been useful for it's not in use for the star cluster studies. So Ramakant, yes sir.
Thanks.
You need this or you have? There is a right.
Okay, good morning, all of you. Today I will talk about before talking about this working, I will give just few overview. What are the CCDs we have used with this telescope? So first CCD was 384 by 576, as I've said that. So it was purchased in 1989, and size per pixel size was 23 microns, and it was giving a field of view 2.3, 2.5, and it was operating temperature was -1 degrees Celsius, and it was our second CCD we got 1K by 1K, and it was installed in 1993 with 24 micron pixel size and field of view was 6. Again, operating temperature -1 degrees Celsius. After that, in 2000, we got 2K by 2K CCD with 24 micron pixel and field of view 12 watt minutes into 12 watt minutes. Again, it was also we got another 1K by 1K CCD, 1340 by 1300 pixels, and it was purchased in 2015 with the pixel size of 20 microns and field of view 0.5. It was also an institute. This CCD is still we are using this 1340 by 1300. So with this first CCD 384 by 756 pixels. First observation observation was done by Dr. Mohan in 1992, and this was the first paper produced by them, and they observed open cluster Q10 with the aim to find out the parameters of this cluster. This is the first image. obtained by the 384 by 5 pixels. And this is the colorimetry diagram, what they have used to find the parameters of the clusters. In 2019, we got another PCB, that is photoelectric PCB, and it was purchased by STA USA. And here I put
Pointer cheek and pointer top on that side. So that it doesn't. No, sir. Actually, setup is like that. Oh, it has to be like that. No problem with this. Only he's.
Yeah.
No,
Yeah. The pointer.
Pointer top one, sir. Hold कीजिएगा उसको दबा लीजिए. Yes, sir.
Okay, so this is the front view of this newly acquired CCD. So
people at the end are able to listen to him. Yes, sir.
okay. In the front, I mean, in this diagram, you can see there are many features. In this CCD.
Can you change the pointer style?
Pointer style changes. Make it normal one. It is renewable. That's it. Pointer is like that. No, just take the sticker. Yeah. Stick will know.
So you can see that this is the light vapor to block the light, and this is the shutter. We have bond shutter of size 125 this is the provision to fill the LNP, and we have also another device to stop the telescope goes in upside down. So LN2 is below. So to stop that, we have another device that is called anti removal. If you see the back side of this CCD, we have a vacuum gauge, pressure controller, and vacuum valve is there. This is the to set the tip and tilt in the CCD. We have also provision, and to during the observation in the evening time, we have moisture also comes. So to remove that, we use dry nitrogen, and this is the provision to flow the nitrogen, dry nitrogen. And this is all controller and cables. So this is the specifications of the chip. It is 15 micron, 5 pixel PCD, 4K, 4K, and back illuminated PCD. Equivalent capacity to 50 to 265 kiloelectron. And we have different selectable gains, 1, 2, 3, 5, and 10. And we have option to operate this with readout speed 1 megahertz, 5 kilohertz, and 100 kilohertz. We have provision to select the binning mode, and dark current is very less here, and 0.005 electrons per second. And this is Olympic mode. If we see the quantum efficiency, this chip is blue enhanced CCD. So we use UV Variac filters with this camera of the size 90 mm square filter, and transmission is this. We have filter grid, which is developed in a And there are square slots in the CCD to put the wheel, to put the filters. And to control, we have also developed GUI in eighties. Shutter size is 125 mm, and minimum exposure we can give 10 millisecond. We have characterized this camera CCD chip, and we determined the gain and readout noise using the flat and bias observed with this camera. So basically, we determine that we observed many flats and many bias. And if you plot many counts versus standard deviation, you can determine the gain. We also determine mean relation without noise, and we also check the linearity of the. Okay. Again, we plotted integration time and mean counts, and you can see that it's perfectly linear up to the saturation limit. Here, with this plot, you can also determine what is the film capacity of this. Here I've listed what we have determined, gain, and these values are provided by the company. So it is very similar to the company values. To check the performance of the CCP, we also observed an open cluster, CJ43. 2 images in B and 2 in B filter. We did to the time 5 minutes each. And I mean, there are some defects in the corner. This is basically anti-reflection 14 is going back. With this observation, we plotted this error in 92 diagram. You can see that with this CCD and telescope, we can go to 20/90 plus minus 0.2 error. And this is the telemetry diagram. Basically, this is not, a lot of field stars are there, so we use their data to select the members of the cluster. And this using this BPT diagram, we selected the members, and here we plotted only members of clusters. So, and we determine parameters. So, since we are using 4K by 4K, so what are the things we can do in star clusters? What are the signs we can do it? A cluster being, cluster size is, there are different sizes of clusters. So if you have white filled cluster, so you can observe that, and you can find out the complete population of the cluster using white filled detector. And with this, we can study core and corona of the clusters. Also dynamical evolution, because during the dynamical process, low mass stars go outside. So to find the complete population, we need larger field of view. And if you want to study mass function variation to this process, we will use that. Okay, these are scientific programs which are have been taken using the CCT measure. Okay,
Any question? Thank you, Ramakant, for your nice description of 4K by 4K CCD. But if you have any technical questions, yes. No?
Can be operated at 1 megahertz also. Right?
see, yeah,
The operation is 1 megahertz
for 10 minutes. Yeah,
You can use this mic.
Okay.
So cooling time, we talk about, goes up to 13, 14 hours.
It's the friends करता है
Very high.
If you want to move,
Yeah.
You see the
picked.
impact on the cooling point. Related to what, not noticeable.
I don't think so. I mean, up to 13, 14 hours, I mean, it's continuously minus 120 degrees.
But what fraction of the time are you running at 200 megahertz and 1 megahertz versus at 100 kilohertz? Looking at duty cycle,
Mostly we use 1 megahertz.
mostly one.
Yeah.
So, so the non-linearity curve of the we have taken good sensitivity, so you have taken this.
They give
Not extrapolated. We have observed and we have all the points are observed.
Yeah, you have, but there are not many points. I mean, when you have a lot of points, then you can actually pinpoint where this linearity curve is deviating.
Yeah, but in terms of we have, I mean, at the point of deviation, we have points.
Yeah, you can show that. I think it is there.
Yeah.
Yeah. So, if you linearity. So we have observed a saturation level.
Yeah.
And after that, there is strong deviation.
Yeah, flat.
Becomes almost flat. Yeah. So, but normally it happens that it is linear, then slowly, gradually it goes to non-linear. Didn't happen.
I mean,
Depending on the case.
it's here not lot of points are there, so
That's my point.
Yeah.
If we have more points at that level,
Yeah.
then we can really check when, at which point it is going towards the non-linear.
yeah, here you can. Yeah.
Can we use this molarity curve to monitor star up to high, high threshold value or high counts, so that we can we can observe and we can have the non-linearity values, and then we apply this non-linearity correction, and then we can observe star for even deeper observation, larger observation.
Yeah.
So we can do.
Oh, yeah, Tushiji.
My question is related to this diagram.
Yeah.
Maybe I missed the point. This is based on a single frame, or you take multiple frame, thousands of frame, and then for a single pixel.
Multiple.
Okay.
Flats, we have also 10 flats. 10.
10 flags.
Roughly
And
10.
Then the sigma value is based on per pixel for this 10.
No, not per pixel. I mean, we selected the region, like 1,000 by 1,000 pixels. 100 by 10 by 10, 100 by 100.
So you're not characterizing each pixel, right?
No, because to check these parameters, we need a clear region. Pixels should not be hot pixels or bad pixels, otherwise our value will change. So we need clean region.
That is okay,
Yeah.
but in clean region also, you can have individual pixel, you should have several frames, suppose 100 frames, 200 frames.
Yeah.
Then for each pixel, you have 200 points.
Yeah.
Based on that, you can get signal.
Single pixel, that pixel is perfect. I mean, there is no defect in that. So we can use it.
We are not defect. I assuming things are
Yeah.
working normal.
Yeah.
We're not talking of defect. What is working pixel? So that was my confusion. So it's
Got any other question? No? Okay. Readout time.
Our readout time is depends on the readout speed. Yes.
yeah.
So,
1 megahertz.
1
megahertz. You can. The range from 100 kilohertz to 1 gigahertz. But
Yeah.
then, like, Your read lines depends on the readout time.
Times.
So where you are optimizing? Eh? 1 megahertz.
1 megahertz.
Accommodation is less than 1 megahertz probably, right? So for
Yeah, 100 kilohertz, 500 kilohertz.
about 16 seconds.
Yeah, 16.
Good, Ramakant. So if there are no more questions, let us thank the speaker for his excellent talk on CCD images. Now, there is a small video by Nilakshi, who is located in US, professor at University of Texas, right?
Yes.
Dear and respected Dr. Banerjee, the director of ARIES, Dr. Ramsagar, the founder director, revered dignitaries, scientists, engineers, research students, alumni, staff, community partners, and distinguished guests. I, Nilakshi, a proud alumna of ARIES, send my warmest greeting and heartfelt congratulations to all of you from the University of Texas at Arlington on the 50-year Golden Jubilee celebration of the Sampurnanand telescope, a telescope that I used as a research student from 1995 to 2001. Today, 2 decades later, I'm honored to be invited as a guest speaker to share my thoughts. I wish I could be there in person to celebrate this historic event. Though I'm not there, I'm joining it through this video and my memoir that I have written, and hopefully by attending some of the sessions virtually. I have penned my memoir at length that you will find in the handbook. I hope you find something inspiring on every page when you read it. Today, I'm presenting a condensed version of it in the form of a poetry that I have put together. It is titled A Journey. When I joined UPSO, aka ARIES, my dream, a dream of touching the sky, the moon, the stars came true. I observed the star clusters and studied their spatial structures. I was the first one with my team to observe a GRB's afterglow. How can I forget the mesmerizing nights of Leonid cosmic show, a total solar eclipse, and a long tail of Hale-Bopp on the go? Memories are still fresh of Saturn's occultation and many moments of reflection and contemplation. The outside railing of the telescope was my favorite spot, from where I observed star-studded skies, beautiful twilights, cloud-covered valleys, sounds of cicadas, bell of Hanumangadi, and twinkling lights of Nainital city. But the journey was always not smooth or easy. We walked through relentless rains, snow, mountain fires, and hailstorms that ripped apart our homes and made minor dents in the domes. There were other hardships too. There was no common cafeteria, proper transportation, or easy way of communication. And for the most part, I was the only girl. There was no female scientist, engineers, or role models. But my motivation was strong and I kept moving on. I learned to focus on solutions and enjoy those sleepless nights of observations. Challenges, struggles, and frustrations all seem mundane when the zeal of learning and exploration was on flame. I am thrilled the State Observatory could take a new birth as ARIES. The journey that I started The journey that we all, you and me, started continues. After all, we are merely a link between preceding and succeeding generations. We are here on this earth for a much bigger purpose of exploration. Some seek it through spirituality and some through science, but both teach us we are all connected with a higher power, or you may call it the universe. In the spiritual world, the connection is set through meditation, and in the physical world, it is a telescope that is a gateway between humans and heavens. So next time when you stand in front of a telescope, do not think of it merely as a tool to collect light, but think of it as a time machine or a connector to open deeper realms of our imagination and existence. मुझे बहुत गर्व है कि एरीज, जहाँ पर खगोल विज्ञान के शोध का कार्य 50 वर्ष पहले संपूर्णानंद दूरबीन के साथ आरंभ हुआ, वहाँ पर आज देवस्थल में एशिया की सबसे बड़ी 3.6 मीटर दूरबीन उपलब्ध है और जल्द ही 4 मीटर लिक्विड मिरर दूरबीन का भी उद्घाटन होने वाला है। और एरीज में आज अंतरराष्ट्रीय स्तर का शोध कार्य चल रहा है। उससे भी बड़ा गर्व मुझे इस बात का हुआ है कि आज एरीज में कई महिला वैज्ञानिक और इंजीनियर कार्यरत हैं। यह हम सभी के लिए, खासकर हमारी नई पीढ़ी के लिए प्रेरणा की बात है कि सफलता की कोई सीमा नहीं होती। जिसके मन में पैशन है, लगन है और विश्वास है, वो कोई भी मंजिल हासिल कर सकता है। बीच में बाधाएं आती हैं और आएंगी, लेकिन हम उन्हें कैसे पार करते हैं और कैसे अपने मनोबल को मजबूत रखते हुए आगे बढ़ते हैं, उसी पर हमारी सफलता निर्भर करती है। और आज भारत की आज़ादी, जिसकी हम सब बात करते हैं, उसके अमृत महोत्सव की यही एक सही मायने है। इसके साथ एक बार फिर से आप सभी उपस्थित गणों को संपूर्णानंद दूरबीन की स्वर्णिम जयंती के उपलक्ष्य में मेरी तरफ से हार्दिक शुभकामनाएं व अभिनंदन। धन्यवाद।
Let us thank Nilakshi, sorry, for the wonderful speech that he gave on the occasion. Moving on, we have another talk by Devan Buddhist, and he will talk about study of intermediate age open star clusters. Ready, Dr. Bist? Good.
Good morning to all of you. Thank you so much for inviting me to present my work on Golden Jubilee workshop of Sampurnanand telescope. This telescope is also very special for me because my thesis was based on this telescope. So today I'm going to present my work, study of an intermediate age open cluster. So our galaxy is the collection of large number of stars and interstellar material held together with strong gravitational force. And our galaxy has three basic components to its visible matter: disk, bulge, and halo. In the disk area, some young stars young stars, old stars, and open star clusters are there on the galactic disk. And in the bulge area, some massive clusters or old stars are there. And in the hollow area, globular clusters or old stars are presented here. So open clusters are the group of few tens to thousand number of stars, and they are very young stars in comparison to globular clusters, and they are population type 1. That means higher in metallicity, and may still be surrounded by nebula from which they formed. They are very young too, and are located in the spiral arm of a galaxy. So we have taken observations from 104 centimeter Sampurnanand telescope for many open clusters, and many more. I have listed few clusters here, and this is log of observation for one cluster SEI 35. And this is simple flowchart. What we do after taking CGD data. So our main purpose is to get the standard magnitude and position of stars. Apart from this observational data, I have also used Gaia EDR3 data. In Gaia data, we all know that the photometry, astrometry, and the spectroscopic data for many stars are there. But in case of SEI 35, we didn't get information about spectroscopic observations or radial velocity for SEI 35. That's why we have also used LAMOST DR5. So from here, we estimated a mean radial velocity and metallicity for cluster SEI 35. And this value has been used to obtain the orbital parameter of the clusters. And also, we have also used APSS catalog. We have cross-matched our observational data with APSS catalog. And for this matching, we put difference in position as 1 arc second. And we found some 68 stars matched with this catalog. And you can see the difference in magnitude and color. So our data is showing good agreement with this catalog also. So membership is very important for open clusters, because open clusters generally found in the most populated area of the galactic plane. So this first step to remove all the field region stars from the cluster to identify the more reliable cluster fundamental parameters. So this is vector point diagram for Berkeley 24, and for all stars on the left, in the middle panel on cluster sequence, and on the right side the field motion. And this circle is simple compromise between the losing cluster members with poor proper motion and the contamination of field region stars. So this is preliminary selection of cluster area, and then after we have also estimated membership probability of all stars using this method. And according to this method, every star can be described in cluster star distribution of 5 CV and the field star distribution, where the notations have their usual meanings. And then we estimated membership probability, and you can see this plot V magnitude versus membership probability. And we considered a star is a probable member which have membership probability higher than 0.5. And we have also compared our membership data with Kenton-Goodin catalog. Kenton-Goodin catalog is available with limiting magnitude of 18. So our data is much useful, because at least we are going 2 magnitude deeper than Kenton-Goodin, which is very helpful for the mass function study. So radial density profile, we for the radius estimation, we first constructed so many concentric circles around the cluster center, and then estimated density using this simple formula, number divided by area. And then we plotted radial density profile, log radius versus log density. And a smooth line is represents the King profile. According to the King, basically we need 3 parameters to describe the structure of a cluster: the core radius, tidal radius, and the richness factor. Core radius is the distance from the cluster center where central density becomes half. And tidal radius is the point from the center where gravitational influence of galaxy is same as of star cluster. And richness factor is depends on the internal motion or the dynamics of stars. So we have, after fitting this King model, we estimated many structural parameters: central density, RC is core radius, capital RT is tidal radius, and density contrast parameter also. Interstellar reddening. Reddening is most important parameter to understand the intrinsic properties of cluster stars. And reddening occurs because of the absorption and the scattering of starlight in the interstellar medium by the dust particle. So in the absence of spectroscopic observations, we generally use B minus B, U minus B color diagram for the reddening estimation. So we have used all probable members and from here we estimated reddening at 0.72. And we have also matched our data with 2 mass JHK and plotted various color diagrams. And you can see here, this is the best linear square fitting. And after this fitting, we find our derived ratios are here, and our values are showing good agreement with the normal ratios. So this showing that the interstellar extinction law is normal towards the cluster area. And for age and distance is very most important parameter in the astronomical research. And we fitted theoretical isochron given by Marigo to estimate age and distance. And from here, we found 2.25 gigayear and 1.27 gigayear for these two clusters. And we also estimated distance using parallax from Gaia data. So we also used 0-point offset as given by Lindergrain. And we used the technique given by Beller-Jones for the distance estimation. So we found that the distance value is showing good agreement from the parallax as well as the isochron fitting method. So we also checked the binary stars, binary content on these two clusters. And for that, we first estimated tangential velocity. And then we plotted histograms, and we distributed cluster area into 2 parts, core region and off-core regions, as you can see here in the round figure. And you can see the two peaks are here. One is the larger peaks and one is the lower peaks. The higher peaks is for the single star distribution, and the lower peak is for the binary star distribution. So from here, we found some 13.59 and 14.20% binary content in core region and some around 10% in the off-core region. So I have shown here the binary stars with the red dots, and we have also found blue struggle stars in these two clusters. Blue struggle stars are most integrating object in the astronomical universe, and especially found in the globular clusters or the old open star clusters. So we have found 5 BSS members in 2022, and this information we are giving for the first time in the literature. And in case of Malot 71, already Wren et al. Catalog, they already listed these BSS in their catalog. So we have just cross-matched our BSS member with Wren et al. Also, and showing good agreement. And about the initial mass function, a detailed description was given yesterday by Dr. Saurav, so I am not going into detail. So initial mass function was first quantified by Edwin Salpeter, and this is the power law, X is mass function slope, and Salpeter has used stars higher than 1 solar mass, and they found slope as 1.35. And after that, many astronomers came into action, Kropa, Chabrier, and they also estimated initial mass function for various clusters. But we are not in a position to say that what is the basically the star distribution for massive star as well as the lower mass star. Actually, we can't fit the same power law for the massive and the lower end stars. So, and one more question is raised also here: is the initial mass function is universal, or initial mass function change into environment to environment or cluster to cluster, or initial mass function depends on the other astrophysical parameters? So these questions are open. And now we estimated the luminosity function and mass function for these many clusters, but here I'm giving example of Berkeley 24 and CGNE 27. So first we estimated completeness of the CCD data. Why completeness is so important? Because we may not detect all the stars present in the CCD frame due to the stellar crowding as well as the inefficiency of the CCD data reduction programs. So that's why we randomly added 10 to 15% of actually detected stars to our original V and I images. And then we have done data reduction as similarly as was done for the original images, and then estimated completeness factor. So you can see detail in the paper Yadav and Sagar and Griffith to understand the artificial star test. So this is, from here we found that around 19 magnitude, the completeness factor is around 90%. And the luminosity function is the distribution of star according to their brightness. So we have plotted luminosity function from here using after using completeness of this data. And then we used the theoretical isochron, which we have used for the age and distance estimation. So to convert luminosity into mass function, and we found our mean. So, in good agreement with the Salpeter power law. Clusters orbit, generally open clusters orbit near the galactic plane, where they are constantly disturbed by tidal forces originating from the tidal forces as well as the molecular cloud present there. And due to this disturbance, the structure of open cluster get changed, and orbit is very important to understand the evolution and formation of stars, clusters, or galaxies. So here we have used the model given by Allen and Santillan to understand the orbital picture of clusters. So here, these equations are the galactic potential equations, and on the left side, we have traced the orbital picture. On the left one is the side view, and the middle one is the top view, and the right one is the motion of clusters in the galactic plane. And the solid triangle is showing the birth position, and the solid dot is showing the present day position of clusters in the Milky Way galaxy. So our study, and we have obtained many orbital parameters from here. So eccentricity is coming around 0. That means these clusters simply trace the circular path around the galactic center. Our dynamical relaxation time, we have in one paper we have used two pair of binary clusters. NGC 5617 Trumpeter 22 is one pair, and the rest is another. Distribution approaches to a Maxwellian equilibrium. It depends on number of stars, mean mass, and half mass radius. So it's a little bit complicated to find the half mass radius. So we have used the method given by Larson to find the half mass radius, which is depends on the King model. Actually, in the RC is core radius and RT is tidal radius. We have estimated these parameters in the radial density profile section. So from here we estimated half mass radius and estimated relaxation time. So our study indicates that NGC 5612 and Trumpeter 22 are dynamically relaxed because their relaxation time is less than the cluster's age, and the other pair, NGC 3293 and 3324, have higher relaxation time in comparison to age, so they are not relaxed. And we have also plotted mass segregation. Mass segregation generally depends on the equipartition of cluster members. Actually, during the close encounter, or we can say during the star exchanges both energy and momentum. So energy can be exchanged in either direction. So there is a statistical is known as equipartition, and this encounter begins until the system becomes relaxed. So we distributed cluster stars into 3 different mass ranges and profile. So okay, sorry. So then and we have also checked our result with a statistical test, Kolmogorov-Sinro test, and our confidence level is coming around 88, 75, 77, and 70 for the mass segregation. We have also checked the binarity in these pairs. We estimated the separation of these 2 clusters, and we used the method given by D. Lafleur, which depends on the orbital time period, eccentricity, and the mass of cluster M1 and M2 are the mass of 2 clusters. So S0 is the separation. We estimated separation, which is coming around 18 and 19 parsec for both the pairs, which is not very much. So we can say that these clusters are bound. And we have also, in one paper, we checked the variability in open clusters. We have taken data from 1 meter Sampurnanand telescope. And this is just 1 or 2 night data for these clusters. And from here, we have found some 19 variable stars, and using the periodogram analysis, we found the period range as 0.13 to 0.43 days for these 8 clusters, but for 11 clusters, we couldn't find the periodicity due to the lack of sufficient data. So we are planning to take observations for to search the variable stars in open clusters from 1 meter class telescopes and other telescopes also from 1 meter Sampurnanand telescope, and we have nights in several months from in 1.3 meter GCBT to search variable stars in open clusters. And in ICSP, we have also a small telescope, 0.61 meter optical telescope. We are planning to search variable stars, and we are planning to use ground-based observing facilities in India from 2 meter SCT, 2.3 meter VBT, 3.6 meter DFOT, and also 0.61 meter to observe the transiting events. And we are also we have a spectrograph at ICSP, so we are also planning to do some spectroscopy of bright sources, giant nova, etc. So thank you so much for your attention.
Thank you. Any questions? Yeah.
In one of the cluster, you showed that the cluster has already made several orbits. Okay.
Yeah.
And,
the orbit.
so I would expect some kind of tidal tail. Have you noticed that, or if not?
In these clusters,
This particular, yes.
actually, we didn't find any tidal tails.
Or have you searched that data for a larger area, for example, 3 to 4 times of tidal radius?
Actually, we yeah.
May I ask another question if you can allow me, or
Please.
okay. So in one of cluster you showed that you found binary stars.
Yes,
Okay. My question is, what fraction of binary stars you found, and what
around 10 to 14%.
14%?
Yeah, 10 to 14.
And if you exclude or include, you see some changes in the slope of the initial mass function.
No, we didn't get any changes. We tried it, but we didn't get any major changes in the slope.
But you are limited to certain magnitude, right? Like this.
For mass function?
No, I mean the binary star fraction what you got.
Yeah, we used up to 18 magnitude. Yeah.
Bob, you are pushing.
Sure.
No,
Please.
मैंने पूछने मैं just add करना चाहता actually this aspect is very important.
Yeah.
How this binarity affect the slope of mass function.
Yes.
So for that, definitely observations, you will be not able to get precisely.
Mhm.
So what people have done, they have done simulation.
Okay.
And yes, that's right. And if you happen to read, this was my part of the Humboldt Fellowship.
Okay.
It's in 91 or 92 we have published,
Okay.
and there are 3 effects we have analyzed. What is the effect of metallicity,
Okay.
effect of various proportion on the mass function.
Yes.
So there we have elaborated that how much it can affect. So error part you can see from there.
Okay.
Okay.
Yeah, I will.
Comment on this. See, normally, initial mass function is not expected to change too much because of this binary star. Reason is, at the time of birth, very independently they are taking birth. Later on, dynamical process, due to dynamical process, some of the stars, they become binary because but at the time of birth, they don't.
Joshi,
But okay.
we are running out of time, please.
So anyway, this is just a comment.
Jeevan, last question.
You mentioned that you are applying the Gaia offset in the distance in the Gaia offset 0.05.
Yes.
Why is it so? Why you are applying the offset 0.015?
Actually, this basically parallaxes are not very accurate measurement. Maybe inefficiency of data or
That you
many
measured-
other reasons. So
You measured this offset or?
no.
This Latin
Yeah.
green paper, you mentioned that because people are from the Gaia, that they must have applied this.
The objective offset is mentioned in that paper.
Yeah. So we have just taken from subjected.
Good. So let us thank the speaker again.
Okay, thank you.
Nice talk.
Thank you.
Thank you. Now, moving on, we have a talk by Neelam. Good, women power. Yeah. Yes, please. Good.
चाय कुछ लोगों को चाय नहीं मिल पाई है, चाय बाहर है, तो आप लोग लेके आ सकते हैं और चाय ले सकते हैं इन बिटवीन.
Okay. Right. So, and she will talk about star formation in bright rimmed clouds and young star clusters. Good, Neelam. Go ahead.
नीचे पाँव में ध्यान रखिएगा, अभी यहाँ उधर मत जाइए, इधर आगे हो जाइए, आगे वो दिखाई, ये देखिए ना, यहाँ से देखिए, और नहीं तो यहाँ जाइए,
Thank you, sir, and good afternoon. So here basically I am presenting the work which I have done with the 1 meter telescope basically during my PhD. So most of the work is my PhD work, and after that, so so these are the outlines of my talk. First, I will give a brief introduction and motivation. And the main sites of my study are bright in clouds. So I will also talk about these. And finally, I will talk about the summary and conclusion. So that we know that most of the stars, they form in the clusters, and clusters contain different mass stars, from low mass stars to very high mass stars. And so if there are some massive stars which are present in the young star clusters, by young star clusters I mean star clusters which are less than 10 million year old. And just like here we have this is a open cluster at the center, and IC1848 is, and here we have a massive star which is O7 type star. So when this massive star formed, it ionized its surrounding molecular gas through its ionizing radiation, and so the massive stars may play the destructive role or constructive role. In the destructive role, it may just disperse the molecular cloud or ionize the molecular cloud and halt the further star formation activity. Or in the constructive scenario, it can further trigger the star formation in that particular left molecular cloud. So this is also one of example of example where we have induced star formation or triggered star formation. So we can see that at the center, this is a massive star cluster, NGC3603, and we can also see different population of
Yeah, you can press the pointer.
So here we can see many different generation of stars. So at the center, this is a massive cluster, and we can also see many of these stars. These are in main sequence. We can also see aging supergiants. And we can also see some dark clouds inside which star formation is still taking place. So when the massive star is there at the center, and it ionizes the molecular cloud and propagates the ionization and short fronts. So there are various mechanisms which are proposed to trigger the star formation at the periphery. So one of them is galactic collapse, and the other one is the radiation-driven implosion. So basically, in the galactic collapse model, between the two propagating fronts, the neutral material is accumulated, and with time it becomes massive and fragments and collapse to form new generation of stars. So we can see different clumps different massive star or a massive star cluster at the periphery of the H2 region. So this is the collect and collapse scenario. But in the radiation-driven implosion model, if you see, so there the clumps are already existing, and the ionization. The ionization front or shock front, they just compress the pre-existing molecular clumps, and they induce to their collapse and form the further star formation take place there. So this is an example of collect and collapse model. So here we can see there is a massive clump at the periphery, and we can see most of the molecular material is accumulated here at the periphery. And when we talk about the radiation-driven implosion model, so for the radiation-driven implosion model, bright rim clouds are the ideal target. So these are the small molecular clouds which are found at the periphery of the H2 region. And because they are found to be associated with the young stars like T Tauri stars, Herbig-Haro objects, and also molecular outflows, etc. So they are considered at the sites of the triggered star formation. So in the bright rimmed clouds also, there is a scenario which is called the sequential star formation scenario. Which we have tested. It is that if suppose the massive star is somewhere here, and this is a bright rim cloud here, and when according to this, the star formation process proceeds from the ionizing star side to the bright rim side. So it means that we should get some kind of age gradient when we go from ionizing star side to the bright rim side. So this was a main motivation for our study. So to study the star formation processes in the bright rim clouds as well as young clusters and H2 regions, and to study the evolutionary stages of the stars which are associated with the bright rim clouds, and also to search for the age gradients in bright rim clouds. So for this mainly this work, we have used the 1 meter Sampurnanand telescope and 2 meter SCT. In addition to this, we have also used the archival data from TUMAS and WISE and SPGER. So this is an example H2 region, which is W4 East and W4 West. So here we can also see these kind of structures. These are bright rim clouds, and here I have marked them. So in these bright rim clouds, we have also checked the small scale sequential star formation, and for this, first we try to find out the young stars in the region. For that, we have used the SPGER data, and using SPGER data, we have identified the sources which are in the different stages. So these blue circles, these are sources which are like which are in class 2 stage or T Tauri stage, and these stars in this, they are mainly class 0, class 1 sources. So these are the in the previous stage, in the earlier stages, and we also check the infrared IR axis or infrared axis, which basically shows that how much thick is the disk in young stars, because in the very young age, stars have very thick circumstellar disk. So this delta H minus K, this is basically showing that these stars have a very thick disk as compared to this one. So here basically we have shown the radial distribution of the H minus K or infrared red axis, as well as reddening or AV with respect to the distance from the ionizing source. So here we can see that most of the stars which are like near to ionizing stars, they have less infrared axis as well as less AV, and when we go away towards the we go away from the ionizing source or go towards the bright rim side, we get that that most of the stars, they have a very thick disk as well as reddening, high reddening. So this work we have repeated in other star forming region also. Like this one is IC1805 at the center. Again, there is a cluster, but at this point in this region, we have many more massive stars, and these are the bright rimmed clouds, prominent bright rimmed clouds in these two region, this region. So, and again, this is one another region, IC1396. So basically we have studies this BRC 37, 38, and 39 in IC1396 region. And again, all of these regions, they are associated with the H alpha emission sources or T Tauri stars, or very young stars. And also infrared axis stars, which are again indicating that these are the young star forming region. So basically we have used these color diagram to identify the infrared axis sources, or so these are the JHN based on the JHN HK color, and 3.64 minus 4.5 and K minus 3.6 colors. So each type of like young star at different stages produce different location in these color diagrams. So from that we have got identified the young stars in the region. So basically these are the class 1, class 2 sources, or very young stellar objects in this region. And again, class 0, class 1 sources, which are very young as compared to the class 2 sources, these blue circles. So here we can see that most of the class 1 sources or class 0 sources, they are inside the rim, and these are the outside the, mostly class 2 sources, these are the outside the rim or towards the energy side. Again, we can also see that their distribution, spatial distribution, if we see, it's not uniform, it's a asymmetric distribution, and these sources are aligned towards the ionizing star side. So this indicates the qualitative evidence for the small scale sequential star formation. So to examine the small scale sequential star formation, or S4F, in different VRC regions quantitatively, we have taken the optical observations, and this is one of the VRC region which is observed using the 104 centimeter telescope. So basically, we have divided this region into inside bright rim. This is the bright rim structure here, and outside bright rim region, and we have divided all the young stars which are identified either based on the H alpha emission or IR axis. So inside bright rim and outside bright rim stars. These are for some other bright rim clouds, spatial distribution. So this is basically the data color magnitude diagram, which is based on the photometry taken from the 1 meter telescope. So here, using this CMD, we have calculated the mean age of inside bright rim and outside bright rim region, and we found that in almost all the VRC regions, inside bright rim region was younger as compared to the outside bright rim region. So this was the first quantitative evidence for the S4F in bright rim clouds. So, and we also compare the mass function of different types of BRCs. So basically BRCs are divided into type A, type B, and type C. So type 1 is the initial stage, and if we see curvature of their rim, so it's not that tight. But when we go from type A to type C, so it take a cometary globe-like structure in type C type. So different type of for different type of BRCs, we classified A and BC type BRCs, and we got the mass function. So from this, we found that mostly A type BRCs, their mass function slope is similar to the open cluster, while for BC type stars, they are forming relatively less massive stars. And this is the summary and conclusion of my work based on the 1 meter telescope data. Thank you.
Good. Good. It's open for questions. please. Yes, Riku.
The asymmetric spatial distribution, is there a way to quantify that? Is there a way to quantify the asymmetric spatial distribution?
Because
Can you use this?
when this molecular cloud, it's there already. There are some clumps. So this due to the ionizing radiation, it will be moving away from the from its place.
Just trying to
So
find out, is there a way to quantify the asymmetry? For example, can you
Quantify the
use
asymmetry.
correlation in spatial dimensions to really quantify?
yeah, we can see if we see the larger structure.
Usually, yes. I'm just trying to see, is there a way to quantify that by number?
We can just make a axis parallel to means joining to ionizing source to that BRC, and then see the distribution.
This is somewhat related question, but the role of SNR, SN explosions, do you call more constructive or destructive from the perspective of star formation?
It's mostly destructive if we see if the velocity is very high, but in some cases we have found evidences for this triggered star formation.
Yeah, so that means there is some third factor.
Yeah.
What is that? I mean, in certain conditions, the supernova, a supernova explosion gives, star formation near the rims. And
Yeah, it
otherwise
depends.
it is
It
destructive.
depends. Like here also, if the ion, like it depends on the density of the material also, as well as the expansion velocity also.
Yes, mostly the size of the molecular cloud. What is the size? And then
Yeah,
usually in
yeah.
photo exposure, you have bubbles of hundreds of parsec. So very big molecular clouds you need like to trigger star formation using this exposure.
Yes, in that case, you would expect a different IMF in the rims and outside.
No, but this is not due to the supernova because the regions are very young. It's less than like 5 million years. The regions which are
So the rims are not called the supernova.
No, it's due to only due to the expanding H2 region.
Too young for that.
Yes.
I was asking, any specific reason why BRC type of BRCs are hardly low mass stars?
Maybe because if you see type A BRCs, these form a evolutionary sequence. So maybe in the beginning, the type A BRC, they have more material, so they are forming more more massive stars, relatively more massive stars. DC type BRCs.
Good.
Yeah,
Any-
and at last.
Oh, still some,
Yeah.
okay.
I also thank my PhD supervisor, Dr. A.K. Pandey, with whom I have done this work.
Yeah, it's time to pay homage to him. We lost him in the second place. Yeah. Good to remember him, right? Okay. So let us thank the speaker again. And moving on, we have the last lecture of this session. Kshitij. Wow, Kshitij. And he will talk on young clusters in hub filament systems. Kshitij, horizon to sky. Good. Which one you prefer, this or?
No, I prefer this.
Okay.
So, good afternoon, everyone. Thank you for giving me this opportunity. So earlier speakers have already talked about stellar clusters, young stellar clusters, and evolution of stars. Now, what I will be talking about is one particular topic, the hub filament systems, specifically the young stellar clusters associated with the hub filament systems, and the role of meter class telescopes in modern day astronomy in understanding these hub filament systems. So, first question is, what are these hub filament systems? Can I talk from there, that side?
So first thing, why study Hubble filament systems? Now, the primary motivation for studying Hubble filament system is high mass star formation is not well understood. For low mass star formation, we know that there is an evolutionary sequence which has been established, like class 0, class 1, class 2, class 3, and so on. However, for high mass star formation, it's not well understood, and there are various reasons for it. For example, the faster evolution time of the high mass stars, their rarer occurrence, and in general, they are found at larger distances, that is greater than 1 kiloparsec. However, after various empirical studies, observational studies, a sequence has been established, and the sequence goes overall like this. Like initially, they are infrared dark clouds, which sometimes, or they are massive cold molecular cores.
Yeah, sure.
So infrared dark cloud, then massive, or they are also sometimes referred to as the initial stage as massive cold molecular cores or massive starless clumps. Then there are these high mass protostellar objects or protostellar massive dense core, hot molecular cores, and finally we get these S2 regions which further evolve from compact to classical. So what we are interested in is something called infrared dark clouds. This figure shows an image, MIR image taken from Spitzer. Now in MIR, these infrared dark clouds are seen as dark patches, and on the right is the column density image. So you can see that there is high column density along these IRDTCs. Now, as I said, IRDCs are observed in absorption in MIR. However, at far infrared, because of their low temperature, they can be seen in emission. And most IRDCs, as was obvious from the previous figure, appear as filamentary structures. So they are called filaments, and they often are found to join as hubs. So the whole system is called Hubble filament system. And the classification of these Hubble filament system is empirical, and it's based on column density and aspect ratio. And with the advent of Herschel far infrared data, it has been shown that the Hubble filament systems are there throughout the galaxy, and many stellar clusters are associated with them. So the important questions which we want to answer here is the formation of high mass stars and the evolution of the Hubble filament system itself. On this slide, you can see that there are these various regions which show Hubble filaments. For example, the IRAS 16148, the very popular monoceros R2 region. Then there is this W40 star forming region, which is a close by region. So to expand upon this further, let's look at one particular Hubble filament system, the SS2138 Hubble filament system, and I am showing the image at different wavelengths to illustrate how we can understand that the young stellar clusters and their association. So this figure shows the SS2138 region at different wavelengths. For example, this is at mid-infrared 4.6, then we go towards higher wavelength, and finally the last one is at 250 micron from Herschel. So what you can see is at lower wavelengths, this is at infrared, but the same thing will hold at near infrared also. You can see the stellar sources, and as we go further at higher wavelengths, you can start seeing these filamentary structures. So what you take away from this is that at lower wavelength, you see the stellar sources, at higher wavelength, you see various structures. And if you go at further higher wavelengths, you start seeing, you can get emission from various molecular species. Then if you go at 12 centimeter and centimeter wavelengths, you start seeing ionizing emission, but that's not relevant for us. So I'll skip that part. So now that we know what a young stellar cluster looks like, just a second. What we have to focus on is optical and near infrared wavelengths. Why? Because we are doing it in the context of 1 meter telescope, and as you know, for the purpose of 1 meter telescope, it's diffraction limited for diffraction limited, and you will get only good images only for near infrared and optical, like 0.1 to 0.5 arc second, and the seeing is around 2 arc seconds. So the purpose is served only for optical and near infrared wavelengths. So once we have established that we want to study optical and maybe near infrared from 1 meter class telescopes, let's look at what some of the things which we can do. So don't get confused by so many figures. All of these are color diagrams or color magnitude diagrams. This is not using 1 meter class telescope. These are from 2 meter class telescope, but the point still stands because you have seen in the previous slides by previous speakers that similar color and color magnitude diagrams are obtained from 1 meter class telescopes. So once you observe the various sources, you plot them on color diagram to get the young stellar objects, or on the color magnitude diagram with the isochrones from text, and you try to get their age and mass spectrum, the age spread and the mass spread. So the takeaway from here is you can get the young stellar objects, you can get the age and mass spread, and if for particular young stellar objects you detect them in a wide wavelength range, like optical, near infrared, and mid infrared, and so on, you can also plot their SED spectral energy, and you can get various parameters from models which are available. So let me illustrate how the young stellar objects are associated with Hubble filament system with the help of a schematic. This schematic is from one particular paper, Kumar et al., and this describes one particular scenario of how filaments lead to the formation of young stellar clusters. This is not the only one, but I'm just illustrating it. So as you can see, this illustration shows that they are filamentary structures. They come together and they form a hub, and in the stage 2, and at the hub, due to the high density, high mass stars form, and along the filaments, low mass star formation is going on. And finally, when the high mass stars form in the hub, they evolve and they create obviously ionizing radiation, and the force of the ionizing radiation can impact the molecular cloud. Yeah, so remember in the previous slide, I said you can get the age and mass spread. Now, if you take this scenario, then what this scenario says that low mass stars are being formed along the filaments and high mass stars are being formed in the hub. Now, suppose you observe a particular filament and you are able to get a good detection statistic along the filament, and you plot it on your color magnitude diagram and you get the age and mass spread. Similarly, you can do for various other filaments which you might see in a region, and then you can use that to understand whether this scenario holds in a particular region or not. So with the help of optical studies and near infrared studies, you can understand whether a particular scenario of hub filament star formation is going on in a region or not. This is like one particular scenario, but there are many such theoretical models, and you can see what they predict and what you get. Another thing is the OB stars. Sometimes they are very bright. Like for example, for one of my region, they go in the magnitude like 7-8 magnitude. So you can also get if you can get the spectra of OB stars using 1 meter class telescope, you can get their ionizing output, and you can predict how the ionizing output will impact the surrounding. Like in the previous talk, Neelam ma'am talked about the bright rim clouds. So if a OB star is formed and the ionizing radiation is high enough, how it impacts the cloud and how it leads to formation of bright rim clouds. So for example, this is a region called W40 region. This is again an infrared image, but the point stands that if you can observe this, so this region is an evolved region. It is more like in the stage 4 of this hub filament evolution schematic which I showed. So Since it's an evolved region, you can probably observe with 1 meter class telescopes, and because it has already removed most of the surrounding molecular material. So if you can observe this, then you can again predict the age and mass estimates, you can get the spectra, and you can get the ionizing output and so on. And then with the other data from text, for example, the free emission at 610 and 1280 megahertz on GMRT, you can draw a complete star formation scenario which is going on in a particular region. Finally, various studies of such hub filament system in text are there. Unfortunately, I have not used 1 meter class telescope, but various of my collaborators have used, and I'm just giving some of the examples. These galactic S2 region like SS290 by Manas, S255 by Professor Ojha, then NGC 7538, NGC 6910. These are all hub filament systems. These studies have used 1 meter class telescope. These are not in the context of hub filament system. These have done the different kinds of studies, but since such hub filament systems can be observed using 1 meter class telescopes, the data output from 1 meter class telescopes can be used to understand high mass star formation and the evolution and the various scenarios which lead to high mass star formation. Finally, to summarize, the optical NIR observation can be used to test various theoretical models and simulations. For example, I gave you one schematic, but there are other different theoretical models like global hierarchical collapse, observational signatures in end-dominated collapse of filaments. So where the young stellar objects are formed along the filaments, if they are being formed at the end, then there are simulations which say that this is an end-dominated collapse, and why that is happening, what is the molecular environment in which that can happen. So those kind of things can be said. And the second thing, you can use 1 meter class telescope to get spectroscopic observations. You can understand the ionizing output. You can get the effect of ionizing radiation on the surrounding molecular cloud. Finally, for completeness, though I have not done magnetic field studies, and it has already been explained in the previous talk by Maheshwar sir, but polarimetry can be done, and polarimetry has been done for a lot of these regions, and you can get the magnetic field, especially along the filaments, and you can predict how the material flows along the filament, the longitudinal flow of matter along the filaments, if there is impact of magnetic field on it, and so on. So that is all. This is in the context of what you can do using 1 meter telescope to understand high mass star formation, especially in the with the rise of these hub filament systems with ubiquitous far infrared observations.
Good, thank you. Any questions, please? Yes. Then first.
So you said that the massive star formations are mainly taking place in the hub.
That is one of the models, yes. Not necessarily. There are others which say along the filaments, depending on how much longitudinal flow is there of matter is there. But like massive cores and clumps have been detected along some filaments also.
If we consider one filament, is the position of the hub in that filament varying over time?
No, see, the hub is formed filament. What do you mean position of the hub? In this, if you take observations along different time periods, like different epochs.
So like you can have one filament like this, and you have another filament like this. So is it like they are drifting?
No. This was one cartoon structure. You get different structures of filaments. No, you don't get a different epochs. You don't see that shift. That is a molecular cloud. Like just like I don't think you see molecular cloud shifting over epochs.
Over long epochs, not like. Is it similar to that compression wave in galaxy?
No. Once they form a hole, they entangle.
Okay.
Then they form.
Yeah.
Malik, can you go back to Kumar's model? Stay here. So you are forming two massive cores, okay, and you are like as you are showing here, the bubbles are driven in north or south direction, okay. So why would not I expect a bubble in like east and west direction?
Yes, you can. This is just a cartoon. You can obviously the ionizing radiation will flow all over the place. It will expand in a spherical manner.
Yeah, that's it. Yeah.
Okay. So
This is just
this is the claim that bubble
Yes,
can be expected.
Yes.
Because do you anticipate some sort of flat geometry here, or if
so
it is a flat geometry, then you would expect a north-south bubble.
yes,
Otherwise, you will not.
yes, that depends on the environmental condition. So it's like you have different morphology. Like when you study high mass star formation, the champagne flow, there's the Lister morphology, and so on. Depends on environment.
Yeah, so it depends on the density distribution of the meter.
Any, yeah, please.
Yeah, I think you mentioned somewhere that your scientific purpose met for optical and near infrared both with a 2 arcsecond images. So what exactly you meant? I mean, you wanted more optical or something like that?
So my point was that with 1 meter telescope, if you calculate the diffraction limit for optical, it comes out to be like 4,000 angstrom, 0.1
Okay,
arc
so you are
second.
calculating that way. Not
Yes.
Is there any requirement from a scientific side about it?
So if the seeing is lesser, like they will still you get sub-arc second seeing, obviously you can resolve more sources and you can get a better statistic of ISOs. But even with like 2 arc second seeing, like HCT 2 arc second seeing, here also like 2 arc second seeing, you can do a good science for high mass star forming region.
Good. No more questions? So let us thank you. And let us thank all the speakers of this session. And thank you all for listening to them. And any announcement?
Yeah, I think thank you all. And we will break for the lunch, and lunch is arranged at the same point, close to the 104th story building. And we will assemble again here at 2 o'clock. Thank you all.
Yeah.
For that one maybe.
Yeah.
Good. मैं लेके आ रहा हूँ
मैं सोचा मैं अकेला हूँ जब आए तो 10 दिन
अब सही है
ये पॉइंटर बदला हुआ है अभी जस्ट इंस्टॉल किया है लेटेस्ट वो पुराना वाला तो गायब ही हो गया
Polarimeter then extra galactic tomorrow. वो दे देता हूँ नहीं तो तुम नॉर्मल भूल जाओगे क्या बोलता फेस देख
नहीं तो मैं बोलूंगा वो कहाँ है वो जो बोला नहीं
मेरे को इंटेंशंस नहीं थे ऐसा करने के
वुमन पावर है पूरा इधर
एक्चुअली कल से
मुझे
क्या है कि ऐसी पॉसिबिलिटी है तुमसे करो ऐसा कुछ एक्चुअली सर वो कूलिंग नहीं ले रहा था अभी आज कूलिंग शुरू हो गई है सीसीटीवी जहाँ सूरज बोल रहे हैं कम अर्ली मॉर्निंग देन सेव एटलीस्ट 1 डे
मेरे साथ नहीं काम नहीं करते
करीब 1 घंटे पहले इसी के चक्कर में नहीं श्योर कर सकता लेकिन 11th आवर में सर जावेद जूम से हो पाएगा
कहाँ से
जूम से
हाँ ऑनलाइन दीजिए कोई इशू नहीं है
तो यू हैव अप्लाइड
No, no, I used to hear. तो मैं स्टिल मैं अभी देखता हूँ कोशिश करूँगा कि कल फिजिकली ही मैं फिर तुरंत इसके बाद चला जाऊँगा आफ्टरनून तक पहुँच जाऊँगा ठीक है फिर बात कर लेते हैं दूसरा सर एक चीज होता है कि ये सब हम लोग को सर्टिफिकेट चाहिए यूनिवर्सिटी nowadays they are asking they will not consider our case also they will consider attachment लगाना पड़ता है otherwise next stage में जाएगा
I need to mention the year.
please
पेपर स्टार्ट हो रहा है
2 years ना वो तो मैं था ना तुम थे तो किसी का कुछ नहीं था
और कोई so let us break for lunch खाना खाइए
अच्छा आपका सेकंड सेशन में
जीवन खाने के लिए
अर्चना का टॉक चाहिए
मेरा तो देख सब तो पीडीएफ का कोई इशू नहीं है इसलिए बनाया हुआ कंट्रोल कर दे पूरा देख ऐसा नहीं ऐसा मजाक मुझे स्पेलिंग भी देख लेना
हाँ कल वो मेमोरीज की मेमोरीज
That's what I am showing actually when I show you as paper. Because I am skipping because same reading. And this is a recent result by some paper. Just to show that there is some off between the and I just reporting all the results from the hello. Starting from the comment, we back. Then 16 we did it. Is the other thing. Another work that you started here. These are all the questions that I put. Yeah. Hello. This is another one. Hello. Same thing. Supernova that branches and hello. And this is Aegeans. You are also yeah. This is right. Rakshit is also no, not Rakshit. Rakshit is another paper. Oh, this is Batonin.
oh OJ do it
This is the important things. This is a 14, but written only the 12.
yeah so this is some of them are exclusively on photoelectric
Many of them, these all are exclusively 1, 2, 3, 4, 5. They are only on the polarized. Yeah. And other of them have used the extensively the polarized data. And 2 are from the Taiwan. Sure told me that. That's a good number. 14 is a good number.
I guess there are papers before 2013 also, no? In 2008, also, there was from M4, I saw some papers. For the
Where?
2008, 8, 9.
Yeah, 8, 9, there are many. These are theses. Hello. Okay. Then I started with the upgradation. I started with some upgradation. Hello. Just showing same things. Hello. I will skip every first time. This whatever you are. Hello. It's already ready now. Now the point. Hello. There were different things now. Making the same using UI. Hello. I just got the one polarimetry and I just somebody was interested to do some IR polarimetry. I don't know IR polarimetry. You can do it.
no you
Hello.
cannot do it here
Devastal is
Hello. This side is okay
Hello.
This could be
It would be
Hello.
better if the delay actually.
split or-
Only the point. Only the point here is that the enormous flash solution that is the large amount of. It is on the side dependent. Towards Nainital different towards testing. So my suggestion is that when you do your observation, observe the and the polar.
Hello, hello,
After that, in the same direction.
hello,
Because it will be vanished
hello,
out.
hello,
So either way it will be okay.
hello,
It's nothing.
hello, hello, hello.
And panel description, we have to say that.
Yeah, that
Hello,
I keep on the.
hello,
Appreciate the telescope.
hello, hello.
Elementary for some time.
Yeah, yeah. Only the people come up, then we need to make a
Hello, 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 hello,
survey can be done.
hello, hello.
Right.
Survey can be done so that.
You have already done the hard work.
Yeah.
Like you have
Hello.
already automated things.
Yeah.
Hello, hello, hello,
Only
hello,
thing that you
hello,
mentioned that
hello,
they don't have the grids to separate
Hello.
them out. That would
Hello.
be very good.
Hello.
Otherwise, what we are doing,
Hello.
we are just.
Hello, hello.
Queue stars.
Hello.
Yeah, you could have a nine.
Hello.
It's very difficult. Other thing, the two back.
Hello.
Yeah. It's-
Hello,
Best is split.
hello,
Best split,
hello,
we are
hello.
saying that split the ordinary and extraordinary in two ways.
Hello.
Yeah, even in the
Use
single.
the same city.
Yeah, use the same city.
Hello.
the length of the.
Hello. 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 Hello, hello. 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 Hello.
If you the splitting angle is there, between A and O, right? Splitting angle is more than we want to
Hello.
We are
No, don't put two CC. That is why I'm saying put one CC, 1K by 2.
Hello. Hello. Hello.
You are not
Hello.
going
Hello. Hello.
very far
Hello.
because the wider you go.
Hello. Hello. Hello.
So you have to keep the
Hello.
smaller.
Hello.
At the same time, you keep it in such a way that it can be observed on same CC. May have done something, but it couldn't be materialized in your.
Ashita, I think she's working under you.
Hello. Hello.
She has joined that course of yoga.
Hello. Hello. Hello.
I have
हेलो 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 मेरे भरोसे बता के हेलो हेलो कहाँ पे मैं किस जगह की बात कर रहा था हेलो हेलो अच्छा ये बगल में जादुई लफ्ज जो लगा है हेलो हेलो
That's the situation we can't study in global development.
Right,
So that is
right,
separate.
right.
So there's a just initiative because virus there is just is seven. We can study this. Find the distance towards the stars in different directions, and then this should be
It's a difficult distance of these clouds.
just as often as we are taking.
What is the typical distance?
We are taking in the same line of sight but at different distances. So at one.
Yeah. So with Ishwar, we did the same work actually.
Okay.
Yeah. First, and then
Yes.
then we take the first distances,
Yes.
but use when you think. So that will give some good idea. So check Ishwar's work.
हेलो हेलो
Ishwar,
हेलो
there we use this thing.
This will be really nice and we can automate kind of we require survey more.
Yeah.
So that we
Yeah,
can-
because you have to observe a lot of. And
Right now we have covered two directions, but we are thinking. I have observation after this content. So
oh, so you are observing today or something?
tomorrow.
Tomorrow. Sita was saying that. Okay.
Shared night with
Yeah, yeah.
me and
Yeah, I'm the tax chair for this, so I was going, so next time onwards, I am going to take the proposals very seriously. So write it. Okay, see you later then. अबे ये बैग में यही रखूं? हाँ।
सर ये प्रेजेंटर ये सही है कौन सा
नहीं हाँ डेजर और क्या कौन सा है? एक तो वो था जो हाईलाइट कर नहीं नहीं ये नहीं होनी चाहिए अभी ना हम वी आर नॉट यूज्ड टू दिस टाइप हाँ मुझे बचेगा नहीं बूढ़े बूढ़े जो है ना इनसे सब बचेगा नहीं ये बात तो दिशांकर में यहाँ बहुत इससे क्या ज्यादा
Okay, good afternoon to all of you. Welcome to the afternoon session. So we have 4 people giving us various aspects of stellar polarimetry, which basically done using impole. So first presenter is JC Pandey.
Thank you, Maheshwar. While we're talking on impole, it has been commissioned. Usually it was commissioned 2003, early 2003. But due to the CCD problem that that it has showing that the 2 strips. So it went for the repairing and all, and it took the 2004. So it was delayed by 1 year. It was delayed by a year for commissioning. So I'll start with. Yeah, it's not working. Thank you. So I'll start with overview with the impole. It was commissioned in 2004. You can see the Rotella et al. It was based on the design by Prakash, which was further based on the several designs being polarimeter designs by Appengel, Sen and Tandon and other people. And it is completely made in-house in Aris laboratories. So explaining the impole, you see here that the cutting beam of light, it falls on this field lens, which is up by 6. And with combination of this camera lens, it raises the cutting beam to the CCD plane here. In between these two, then we have for the polarizing element, halfway plate and Watson plate. To get the polarization, we need to get at least 2 Stokes parameter that we call the Q and U. To get the 2 Stokes parameter, we need to rotate the Watson plate by 0 and 45 degrees. So what we do is that you fix the Watson plate and rotate the halfway plate by an angle of 22.5 degrees. Why is it so 22.5? But we need to have a 45 degrees. So this is because the halfway plate gives the phase difference of pi by pi. If we rotate the halfway plate by an angle alpha, the plane of polarization vector will rotate by an angle 2 alpha. So it's rotating easy to halfway plate other than the Watson plane. So we rotate the halfway plate and gives the 2 values of the Stokes parameter. Here the Watson prism is kept as a parallel of the telescope, north-south of the telescope. And the axis of the halfway plate is also parallel to the axis of
Wilson prism, and they are perpendicular their optic axis. And finally, you put the filter assembly just to get the polarization in different band. Here is an image. No, it's not showing that. Okay. Here is an image just to show that two orthogonal elements that are coming out from the Wilson prism, different colors. You just see that this mirror image of this. So what you do is that to get the value of ratio, that is, I just mentioned the difference of two orthogonal images, then sum of the two orthogonal images. That will give you that R alpha, that is depending on the angle, is equal to P cos 2 theta minus 4 alpha. So if you rotate, as I mentioned, is that, so measuring two Stokes parameter at angle without rotation of the halfway plane, and this is a rotation at 22.5 degrees, so that we will getting that 45 degree of the rotation of the Wilson page. So we will have the two Stokes parameter at R0 and R22.5. So getting the polarization P is equal to, since Q is equal to P cos theta, or to U is equal to sin theta. So we get it, E polarization is equal to root of the Q square plus P square, and position angle is theta is equal to tan inverse Q upon U, 0.5 tan inverse Q upon U. Even you took the additional two values just to rotate it, just to get the reverse Stokes parameter, so that you will have a minimum four data point just to fit this equation. So to get the value of the P, that is the polarization, and theta is the angle of polarization angle. With this, then I will come to the science result that has been done since last 16 years. A range of cosmic sources are being observed by INPOL. These are the comets, starting from the comets, then active stars, solar type basically. We also observe the CVs, massive binaries, and B stars. The extensive work done on the stop-homing regions that you have been seeing in last day talk by Maheshwar and next talk by Archana. And star cluster, which are the previous one that is basically done is just to study the magnetic field structure. And the next one, star cluster, I observed just to get into the dust properties for the direction of that particular cluster, which were the shape, size, and alignment talked by Sadhana and Namita. Then you will see that. And not only it is limited to the galactic sources, it's also observed also the extragalactic ones, supernovae. You will see that talked by Brajesh tomorrow, and the AGNs also. So I like briefly highlight the results. The comets, this work is done by Assam University people, like HS Das and others, their group. Here, this is the comet observed on two different dates. So why I'm showing is this. You see the variation of the polarization. This is the polarization map. This is they've done the polarization of circular polarimetry, aperture polarimetry. The different aperture, they get the polarization values, and they mapped it. You see the variation of the polarization here on this for December 4 is a different, and here is a different. If you see the average value of the polarization, the P varies minus 1.4 to plus 2.8 for this comet, and in other comet, this is from minus negative to this positive, these values. And this is at the phase angle of the comet of 13.1 degree, and this is around 27 degrees. The two different orientation of the comet, they will get the different value of the polarization. Coming to the another topic, that is active star, that basically I did it from here. In 2009, when we decided to observe this one fast rotator, which has a rotation period of 10.1 hour, and its activity was on the supersaturation regime. So activity, whatever the you rotate, its activity is not going to increase. So what we see that the polarization, this is a polarization in different band, and this is its rotational phase. It's a rotational phase dependent polarization. We try to model it. We see that this is a theoretical value that is obtained from the magnetic intensification of the polarization. That depends on the size of the spots on the surface, which is non-linear dependence. And
This is showing the very small value of polarization with respect to the whatever you observed. And top of that, it's a variable, it's not a constant. So ultimately, we found that if the polarization is there, there has to be some spheroidal envelope with the optical depth of 0.1 to get that much of the polarization. Either is this, or second thing, for a 6 month, maximum 6 month time of this. Okay, so they with the rotation, the symmetry is producing the variable polarization. Another we did by the Manoj Patel, and then he did a dozen of the active dwarf stars, which are either binary or single star, and so that what is the origin of the polarization in these stars. He found that this is a wavelength dependent. We can see that all the stars that is wavelength dependent, and the theoretical values of the polarization which are due to the magnetic field or due to the spots on the surface of the star is shown by this blue line, and this is red one is due to the scattering. So if you sum up this, then either you will get the polarization will be more polarization, and maybe the depolarized too. So in maximum of the things, you get the maximum of some of these polarization. Then they found that the polarization is primarily due to the sum of the polarization of the magnetic intensification, that is because of the spots and getting the symmetry there and the scattering there. And this is the distribution of these stars. Then you see the maximum median value is around 0.16 in the B band and 0.04 in the R band. These are other stellar objects that has been observed using the import. W masters below this here that he has observed and found that it is also the phase dependent, and the probable explanation is that it's because the mass is transferring from one object to another objects. As a gas stream is there when we are rotating, giving the symmetry on the orbital phase and giving the variable polarization. Similarly, you will have this massive binaries. One student, Bharti Arora, that she did his PhD on this, and we found that this was again variable with the binary phase. This is one star DXF. She also found that variable with the binary phase, and could be because could be due to the blob, the mass. Wind has some blob things, giving us some asymmetry, and this is a possible reason for having that much of the polarization here. Another one is intermediate polars. They are the magnetic fields, high magnetic fields are there. So cyclotron emission is there. So this is also the phase dependent here, if you see that. So we also found that these are the other objects. The extensive study was done on the study of the ISM dust properties from this instrument. We have observed several clusters. The list of the clusters are here. And these are the location towards the galactic and the center directions. And the aim of to observe this cluster is just to know that what is the properties of dust towards that direction and what is the alignment mechanism of dust towards that direction. The detail given by the Sadhana here in the right top. I'll just highlight the result here. This is the polarization map, I would say, towards the longitude versus galactic latitude. And you observe these all the stars, all the clusters here, then we found that if the clusters are close to the galactic plane, we found that there are several layers. Minimum one layer of the dust is in front of them. However, when you go away from the galactic plane, the dust layers are not there in front of these clusters. Even if the polarization, you see that polarization is also going to decrease when you go away from the galactic disk, from either minus direction or plus direction. Even if there are some few star forming region like this is the Pleiades region where you can see that more polarization value. This is another thing that The people here started, Maheshwar and others, Archana and Ishwarya. This is a work of Ishwarya's recent paper in 2019, where they tried to understand the polarization magnetic field structure on the star forming regions. This is one of the dark cloud. These are the polarization vectors overplotted over the color composite image of the GHK color composite image, and this is the CO maps of the different intensities. And they found that the magnetic field are more organized and exhibit a small dispersion of 12 degrees. The other results are somewhere here, I just mentioned here. These are some few papers I mentioned here. If I see the same things, then this again the students from the Assam University then seeded the CCC collected the different cometary globules and see the difference between the envelope magnetic field and the galactic plane is varying with the galactic longitude like this. So one object is here, but we have the student doesn't have data in between this. And see if it is the second order polynomial is nicely fitting here. This is the exclusion this and this is the inclusion. There is a no difference in the not much difference in the this correlation coefficient while including and excluding. So this is not only limited with the galactic one that I said that the supernova studies has been done and different thesis has been also completed with this. This is the one example of the supernova 2012 AW. Then we see this is a long-term variation of the polarization and polarization angle. Then Brajesh, he did his work in his thesis also, he found that the variation polarization, the degree of polarization indicating the variation in asymmetry either in the ejecta or surrounding medium. In another results by Sashi, that M-pole or band monitoring of this indicate the signature of the asperity in the ejecta. These are the results. And the results are also found in these papers. Here one object DLAC, the famous Blazer 2F7, it has been also observed during this rare stage or after its outburst. So you found that the evolution of degree of polarization at different stages. Here is the ARIS data point this and this along with the other telescopes data point of the polarimetry. Then these are the theoretical curves that are following to the outburst things. And later on, the polarization was found to the 6 to 32% in this same object by Sube in this paper. So these are the several several objects that has been carried out from the import study. Then if you see the publication things, then we show there are 57 publications. Most of the publications are well reputed journal and international reputed journal. And this is a fraction of the different topics that has been done. You see that the star cluster that is ISM studies and magnetic field structure, they are entirely dominating in this thing. And supernova is increasing here again. And if you see the thesis, there are 14 theses which has been carried out, either partly use the data or fully use the data. And several students like Archana, Ishwarya, Piali, and they have entirely done this thesis from data from this telescope. I mentioned only the 12 minutes, there are 14 theses. The two theses, the two theses is from the Taiwan, this NCO, National Central University from the Taiwan, that is completed using this data. So this is the work. So this actually encouraged us just to declare this thing, polarization, because for the polarimeter, because the older CCD is going to be degraded. This vacuum was also emitted, it's degraded. So we bought a new pylon 1300B CCD and characterizes. These are the different parameters of the CCDs. And other one is a replacement of, we have a sliding filters in the polarimeter. Now you would like to have the automatic on the rotating on the wheel in the polarimeter that we are doing. So just briefing the characterization of this, that we just verified the readout noise and gain, whatever they have provided using this, and found the bias counts with just variation of the bias counts in the different readout rates, and found that is a 0.92% of the 16-bit AY converter. And this is a variation of bias and dark range with temperature. Then we found that around the -80°, it is become stabilized, the current becomes stabilized. The recommendation is just to use the readout rate of less than 1 million hertz, not more than that, because the readout noise is going to be high. Gain either 1 or 4. There are 2 modes of it, or high sensitivity mode and high capacity mode. So you can use 1 and 4. That is the recommendation. Otherwise, other experiments are still going on. So operating temperature should be always less than -80°. These are other things. That's just to get the dark current value, that is 0.2 electrons per pixel per hour. Almost constant and constant bias and dark levels at a different setting of the readout noise and gain. You just see that different binning and different settings. We can use that. Different binning and different can be used. This is the linearity. Then we just found that linearity is up to its full well capacity, and this non-linearity is approximately 2% here. And here the peak quantum efficiency curve, that is around 95%. The other thing is that we just upgraded the filter assembly here. Here is the filter response that has been recently measured by us, by our optical lab. And here are the parameters of the central wavelength and their bandwidth. And this is the filter assembly newly made filter assembly. This is the CAD view, and this is the original view of this assembly. So we will be testing this in this observing season. So it will be remotely operated through the computer only. So the direct drive filter wheels are here, and we have 7 mounting holes. The 4 UVBRI, one is for white light, and one is left here that I'm planning to have a narrowband polarimetry with this. The polarimeter, this entire polarimeter will look like now. We have now different filter fins, and this is the CCD. And the control system, we are trying to change it, just making it a similar one control place. Currently, we have a control place. So everything will be through the one computer. So even if the halfway plate, we have just have a push button that is changing of the rotating of the halfway plate. Now we'll have this UI based either filter control or a halfway plate control. So just to get to the future perspective, then we have done the linear polarimetry. Just would like to do some circular polarimetry. This is I'm giving just one science case. You just see this is a magnetic series where the polars, for example, of the one polars, because the near of the void of the material is fully ionized, producing a highly polarized cyclotron emission due to the presence of the strong magnetic fields, and this is also the linear. This is also the orbital phase dependent. The linear over the circular polar that will also give you the angle between the rotation axis as well as the magnetic axis. The variation of this with the orbital phase will just give you what is the orientation of the orbital phase. So that kind of the information can be determined. Even if by modeling these things, cyclotron emission things, then we can estimate the magnetic field here. So these are the things that can be done. Other example that other measures of told yesterday. So that is also can be done. This is my summary that MPOL is being extensively used since its commissioning. Several science cases has been carried out using the MPOL. Majority of them are the magnetic field structure, dust property using the star cluster and performing regions, active stars, supernovae. It was upgraded 2007 by these people, Maheshwar and others, just replacing the big electronic system with the small one. And now the newer recent upgradation was upgradation of changing by CCD and replacing all the filter the assembly. And we have characterized this. So I'd like to thank you to all, and special thanks to these people. Professor Ramsagar, who initiated this project and who was the director here. Dr. Rotela and Dr. Joshi leading the project because I have worked with them. Even then I have a nice story with them that once, because you don't have a vacuum to bring the CCD after filling the liquid nitrogen from 14 to the optics lab in the old building. So I was holding this with my wrist and he was scolding me, why are you doing this? I was thinking that he was thinking this is the wrong thing to do that. It would have made some things. It was not that, because the GRF interview was going on. The GRF, the people who are giving you the coming for the interview, they are looking you. They will go away. So, and then I love that. This was a nice story that because the optics lab was down and LM2 were there. So electronics, the late people and Artsipant was here today. They were involved, and optics, KG Gupta ji was here, but not here now. And Mr. D.S. Rao was also here. And mechanical, K. Gupta, Inderlal, I just put the commander because don't know the other people that they have worked. So thank you very much. I would like to thank, I'd like to thank the other people who are in midway. That's like Maheshwar and other people who will take up this.
Yeah, I think thanks, Jeevan, for a wonderful, overview of the impole. I think what I would like to mention here is that when I came here as a faculty, Jeevan, as a part of his PhD thesis, has done the calibration for this instrument. I think that should be appreciated well. So with that, any questions? Yeah.
Excellent. My question relates to the laser CC 27. Is there a published result now?
Yeah.
So my question is there a temporal offset between the peak of the polarization and the continuum in that outburst? Exactly. Does it coincide precisely?
Light curve.
Yeah.
So where is the
peak impole? Impole one is here, this and this just following the thing. These two curves, they have shown that the thermal and non-thermal things of the polarization. This is paper by what
Suvendu may be able to.
Suvendu may be able to answer it whether it's here or not.
Okay.
Good answer.
He just saw that internet.
Do you use achromatic half wave plate? Or what kind of half wave plate?
Yeah, it's achromatic. Otherwise, it's achromatic is between 400 to 700 nanometers.
Second question, we are different question. In this cataclysmic variable, you said you showed the polarization variation. But did you check the polarization angle also? Because dust symmetry may get changed.
I didn't check this. So we didn't check this at the moment. That needs to be done actually. The second thing is that I didn't show here that how fainter we can go actually. The two things it depends on the value of the polarization and the number of photons you are getting it. So the value of the polarization, if you have a larger value of the polarization, then you will get easily deducted even if the 16 and 17 magnitude. So the lower value of the polarization, the errors are too large for the magnetic series.
14, 15 magnitude is okay.
Yeah, it's basically 16 magnitude that I was. There are few up to 14 magnitude.
This U filter is new one, or because we are using VBR.
No, this is the older one. Actually, I saw that the U filter, you are not using the U filter because of its low transmissions. Yes, I saw the diagram. I just show you. Yeah, you see that because of very low transmission, so you don't use it. Otherwise, being the UVBR always good for the getting the interstellar polarization.
Yeah, that's property basically.
Yeah,
Right.
Two things are against it. One thing is suppose you have stars later than A, where energy will be less here. And on top of that, quantum efficiency is minimum. So both things getting together, it reduces your threshold.
But having a multi wavelength observation always helps to constrain the the dust. Yeah, because the fitting will be much better. So, yeah,
I think comes.
I agree with you. Absolutely.
This is on your last slide. You had this dream project to do circular polarization.
Right.
So the angle of between line of sight and magnetic axis, typically, since you're not resolving the object so precisely, you are averaging over multiple angles. Would you really see a net polarization?
Yes,
you do. I mean, this is data I have not followed, but maybe you could do it as a function of phase.
it's a function of phase. It's a
But
function
very
of phase.
broad, right?
That's what I'm saying. It's a function of orbital phase actually. So you have two things. You have two things as a function of the orbital phase entirely.
Right, but it's what I'm saying is at any instant of time, you're integrating your data over many angles.
Yeah, true. That's true. That is the
Theoretically, it
limitation.
all looks good.
Yeah, that's good.
Observationally, you're going to be challenged by that.
Yeah.
But has that been shown to work?
There are some estimation that I would say, it's not exactly I would say that you are getting it in. There are some estimations doing this.
But over a 2 pi phase, you will still be able to say some level.
Some level. Yeah.
Yeah, if there are no more questions, let's thank the speaker.
The next talk is by Archana Som on magnetic field mapping using polarized view of ISM. A journey started with 104 centimeter Sampurnanand telescope.
Good afternoon, everybody. So first of all, I thank organizers for giving me this opportunity to show my work here. Is this working? It's on actually. Do what now? How about now? Yes. Okay, so I started my journey here in Aries as a PhD student, and I started mostly my observations on aim pole. Thanks to G1 for showing all the overview of the instrument, and also thanks to Meinel also for giving an overview of the importance of magnetic fields in star formation. So I'm going to show a general overview. I'm not going deep into the results. So my talk will be an overview of importance of magnetic fields, problems addressed and facilities used, findings, and takeaway points. So I'm showing this picture here deliberately because you can see that in early 20th century, many of the Europeans wanted to come to US, but there was some constraints that only few % were able to reach. So this is the analogy I'm showing because our galaxy has a lot of gas and dust, but the star formation rate what we get is a few %. Why? So there may be reasons behind that. That may be turbulence in the interstellar medium, negative feedback. We were talking about negative or positive feedbacks in the morning also, and magnetic fields. So the third culprit may be magnetic field. It is either regulating by enhancing or prohibiting or delaying the star formation in the galaxy. So that's why I gave that analogy. So because I'm talking about role of magnetic fields in star formation or in interstellar medium, I'll start with the big picture. So the big picture says is that magnetic fields play an important role in energy flows at many scales. So if you start with this beautiful image taken by Planck satellite, this is a dust polarization map of all sky, where you can see the dense structures and the magnetic fields shown as the line integral convolution patterns. And the density structures have mostly magnetic fields going along with them. So magnetic fields on a large scale plays an important role by regulating the flows from the center of the galaxies, like having bipolar outflows from the galaxies as on the larger scales and also on the smaller scales. Another interesting thing is if you see the magnetic fields towards the center of the galaxy, you see that mostly the stars around the black hole are mostly connected by these magnetic fields. And the big triumph into 2021 was mapping magnetic field in M87 black hole itself. So this is the larger picture. When we go towards the star forming regions in our galaxy, I'm just showing highlighting the dusty structures as well as their corresponding magnetic field patterns taken by Planck, and these are the main star forming regions we generally study in our galaxy. Okay, so this was all about the large picture and where we are interested. So if we go to the models made by various people, but there was a recent one published in Nature Astronomy in 2020, based on the observations at different scales. And these scales are mostly in the star forming, high mass to low mass star forming regions. It has been claimed that magnetic fields help in channeling the material, and they're towards the hub-like structures in the interstellar medium. And then there we have the star formation activity later on. Observations prove it. In the same year, a Nature Astronomy paper was published by Tushara, where we do see, yes, the magnetic fields are kind of helping channeling the gas going towards this Saturn's main hub filament structure. These were far-infrared polarimetry observations. So up to now, I was just showing the overview why magnetic fields are important and how I started this journey. But where I started this journey will come from here. It all began at 104 centimeter telescope in Aries. And most of my work was on this instrument, AIM-4, which is Aries Imaging Polarimeter. So how the journey started? The polarimeter was here. I joined Mahesh, and Mahesh was taking care of this instrument and doing things. So I was told that let's start magnetic field investigations in our own interstellar medium. So I put more than 10 proposals throughout my PhD on this instrument. We observed more than 20 nearby star forming regions, galactic star forming regions. We did more than 300 hours of observations throughout my PhD. And that produced more than 19 publications with these proposals and with this whole effort. But when I moved out, the AIM-4 results were not enough because that was optical polarimetry, which was only capable of tracing the magnetic fields in the lower density regimes of the star forming region. I got an opportunity to get to submit proposals in East Asian observatories for some millimeter polarization towards the same regions. And later I got an opportunity to propose for the far infrared polarization at Sophia, which is a flying observatory. Apart from these three main observatories I used in my research, I also used near infrared polarization from Sarpol, which is a southern facility, and also from SMA and ALMA. So this was just a journey of observations I started, and then I'm going to show you the scientific investigations we did. Generally, people show the pictures of photos of their students. I'm showing the photo of my bosses I'm going to show. So, so the first question we started in this journey was on the galactic magnetism itself. How the magnetic fields are important at different scales and in different environments. So this was the first question we addressed. So in the line of this question, we selected some nearby star forming regions, especially where stars are forming, protostar cores are there, and starless cores were also there. So the motivation came from the AIM-4 observations, and then we tried to connect the magnetic fields what we got from the AIM-4 at outer periphery of the star forming regions to the larger scale magnetic fields using the Planck satellite in some millimeter, and using KCMT again in some millimeter. We tried to connect the magnetic fields at different scales from subparsec to parsec scales. We did find that there is a kind of change in the magnetic field morphology when you go from the larger scales to smaller scales. And also, I haven't put the numbers here, but the magnetic field strengths were also found changing drastically from outer to inner directions. There is another problem we addressed on are scales important or not. That is a high mass star forming region. The previous one was a very low mass star forming region. There is a high mass star forming region, and this has a very interesting shape of infrared dark cloud or a filament. So we started looking Planck. We went to the submillimeters, to the higher density regions to map high resolution polarization magnetic fields. And then we went still deeper in the center part, which is more high density using the facilities Karma and SMA. We did find that there is a drastic change in the field morphologies going from outside to inside, and the strength were also found changing. The second sub-question in this question was that whether surroundings are important or not. So we wanted to see whether the Needham showed some results on the expanding H2 regions. So we started with this question that whether the evolution and the shape of the clouds in these expanding H2 regions and the pillars, do magnetic fields play some role in the formation of these clouds or not, or is shaping these clouds? So you can see a recent result published in 2018 that these pillars of creation, everybody must have seen this picture somewhere. So these are M16 pillars, or also called pillars of creation. The magnetic fields are found very beautifully following the pillars, but at some regions it is found kind of scattered and changing. So the change in the field geometry is not highly, you cannot see it in here, but if you go to other regions such as 30 Doradus, which was observed in far infrared polarimetry, we did find that due to the presence of this O-type star here, the magnetic fields in both the directions are kind of shaping themselves with the cloud shapes. Similarly, this was part of my thesis, this one. We observed this cloud IC63, which is in a nearby H2 region. And we did find that the high energy radiation coming from here, from the cyan arrow shows that, is kind of shaping this cloud. And with that shape, magnetic fields are also taking a shape. So yes, surroundings are important. The second question I started in my first postdoc in South Korea with Dr. Chang-won, where I got an opportunity to work on some millimeter telescopes where we can do multi-line multi-tracer observations for finding the gas kinematics of these regions. So we had polarimetric information. We wanted to have the gas information. So there we had some observations such as CO and C80 and many other lines. And we kind of compare the magnetic fields or the magnetic pressure overall in these regions to the turbulent pressure. And we found that in this one, which was part of my thesis, we compared the turbulent pressure and the magnetic pressure. And we found most of the time it is comparable. But in some regions, for example, this second cloud, BRC37, this one, the BRC38, the magnetic pressure is very high compared to the turbulent pressure. The other work was done by my student in my postdoc, in my second postdoc. She was using C+ emission. The C+ emission is evident in these regions only, which are in the neighborhood of high energy radiation. And she was trying to compare the magnetic field morphologies with the gas velocity gradients. And we did find some correlation, but the resolution of the polarization was not enough for this investigation. And the third and very beautiful thing what I'm going to show you is the magnetized turbulent flows. We have heard about the turbulent flows, we studied that, but magnetized turbulent flows are important to understand how these long filamentary structures are formed and how magnetic fields kind of give them or shape them in that structure. So this is the work published by Planck, by using Planck satellite by Guan Solar. And these are the two equations we are using to do the investigation in this competition, magnetic pressure and turbulent pressure. So in 30 Doradus again, we color-coded the turbulent to magnetic pressure in such a way that you can see where the turbulent pressure is dominating over magnetic pressure in 30 Doradus. And it is again here in the near vicinity of the O-type star. So which shows that the radiation, the high energy radiation from this star is capable enough to make the surroundings more turbulent. Third question, I started my second postdoc. That is about the understanding the dust grain alignment. If we don't understand dust grain alignment, we don't understand magnetic fields. That is for sure. So that's why this is kind of a back story. Somebody should start from here, but I got a chance to work on this in the last stage. If you don't understand the dust grain alignment in the interstellar medium, which is the cause behind polarization, we won't be able to interpret our results. So BG worked mostly in theorizing and also investigating the dust grain alignments in different environments of the interstellar medium. So I was given this responsibility to use all my polarization data and to help constraining the available theories and models on the dust grain alignment. So the background in this picture is nothing but the interstellar dust, what we have seen actually. So as I'm talking about dust grain alignment theories, this is a summary of all the theories right from the 1949s where polarization was made. Okay, just 2 slides. Made like a very it was available to everybody. So these are main theories, but the most promising and most reliable theory these days is the radiative torque alignment. I'm not going deep into the theory because it takes more time. There is a theory which was established and also lab tested. So we wanted to test this theory using our observations, and some of the observations were taken from AIMPOL. So AIMPOL data played an important role in this investigation actually, because this all started from using the AIMPOL data first time. So in this plot itself, I'm showing you how the polarization efficiency goes down towards the high density regions. So there are cores where stars form, and they have low density envelopes and high density inside them. When we measure polarization from their envelope towards the high density, the polarization goes down. And why so? Because the grain alignment pattern changes and grain alignment efficiency also changes. So that was the one problem we were working on in light of grain alignment. And the reason for this drop in polarization may be the angle of the magnetic field itself, because magnetic fields are responsible for the alignment of the grains. And change in the grain properties, maybe they are getting more circular because we need asymmetric grains for the alignment. And the third thing is decrease in the interstellar radiation, which is all around us. So that is another crucial thing for the grain alignment in ISM. Second, this is the last slide. This is not second last slide. So the second problem we are working in the grain alignment is that how grain alignment is varies in different environments. So we chose carbon-rich and oxygen-rich stars, and we saw that how the polarization pattern changes from being radial in carbon-rich to being a little non-radial and bipolar in oxygen-rich. So the reason might be because carbon-rich grains are diamagnetic in nature, they don't have free spins. They do not get aligned by magnetic fields. But oxygen-rich grains, being paramagnetic in nature, can be aligned by the magnetic fields. So one is totally independent of magnetic fields, another is totally dependent on magnetic fields. The polarization patterns are different. Okay, so takeaway points from the first question. Magnetic fields are found regulating the star formation in our galaxy, and its properties modify with scales and but at some places where the environment is very harsh, turbulent pressures can take over. And the third one is dust grain alignment efficiency decreases towards higher densities in the star forming regions, and they vary with the dust compositions also. That's it. Thank you.
Yeah, thanks, Archana, for nice talk. So we can have some quick questions.
Two questions. I have few questions. See, in general, in interstellar medium or in cloud, the grains can be mix of silicate based or carbon based. Right?
That's true.
So what kind of fraction you consider?
mostly the interstellar grains what we have where we get polarization are mostly silicates. For getting this variation and that what is happening to the polarization, that's why we chose these AGB stars because they have different dust compositions. So, but mostly silicates.
Also, some are
Silicates. That's what I showed. Yeah, but mostly silicates.
The second question is that alignment, magnetic field alone is not responsible. Sometime in the star, when the wind is there, that wind also aligns the grains.
That's a very good question.
So
do you
consider that?
Yes. So AGB stars, especially in the carbon stars, magnetic fields are not going to play any role in alignment of the grains. That's where we consider either enhanced radiation from stellar waves coming from the center or something else. That's why the patterns of polarization what we are getting may be radial because that's going with the stellar winds. Yes, that is called mechanical alignment.
Short question. You are talking of turbulence, right?
Yeah.
So you're talking of micro turbulence or what kind of turbulence you're talking?
These are like large scale turbulences.
Ramp pressure or
Yeah, RAM pressure also. Mostly RAM pressure in these regions.
So not the micro turbulence.
No, in micro scales also we did some investigations.
No, micro turbulence is thermal in nature.
Yeah, but mostly we are using the regions which we are considering are mostly the turbulence created by the O stars and variation, and that is mostly RAM pressure.
Question, you were able to measure the strength of the field?
Yes. Yeah.
So 30 torals. What kind of numbers are you getting there?
Oh, 30 nor, if you go from far infrared 2 millimeters, we were getting up to milligauss. Yes.
And one last question, what is the weakest field you can actually measure, keeping in mind the mechanical patterns?
There, we could go up to less than 10 microgauss also. Yeah. In some regions.
You showed a nice cartoon picture of how filament system and magnetic fields and the alignment with the filaments.
Which one was that?
Yeah, so back again.
Oh, in my introduction?
In any way, I can ask it.
You can come, you can go there. This one?
Go back. Yes.
This one, yes.
So if I see the hub filament system and filaments going matters to the hub as a 3-dimensional. Okay, the filaments coming backward and also they're in all directions. So should I expect a chaotic magnetic field inside the hub, and it should not be ordered with the large scale magnetic field?
Yeah, that is certainly possible because whatever information I'm giving to you, magnetic field is 2-dimensional, it's projected. Yes, that can be possible. But in these systems, especially if you go from the Planck scales to the filament scales, the magnetic field change their morphology a lot. That can be from very highly regular to very highly chaotic.
For example, for the formation of these filaments, you have to have perpendicular magnetic field. That's how you activate.
Not actually these filaments because these are the internal structure. But if you see the filament itself, for example, I can show you in this one. See, so the scales are the scales are compared here. See, so mostly it's being from parallel to perpendicular, the high density region. So one thing we should keep in mind in the light of with the advent of this Planck results, Planck has found that mostly filamentary structures have magnetic fields perpendicular to them where the density is high and parallel to them where the density is low. So it has been seen that
is
but large scale it is mostly perpendicular. But filament scale it's mostly parallel.
Yeah, that's because you have a gravitating hub, which eventually takes over and pulls everything.
So, are these magnetic field lines caused due to the motion of the gas, or are they caused due to the stars?
Okay, so you're yes. Okay. The question is from where the magnetic fields come in this region. So initially these are from the seed magnetic fields and the dynamo motion in the galaxy itself. So that enhances the seed magnetic fields. From there it comes in the galaxy, and it is everywhere. Yes. So I mean, in these regions I'm talking about, these are very, very, very small regions compared to the galactic scales, but they come from the seed magnetic fields from the galactic dynamo motions.
Thanks.
I have.
Lose some. Sorry. See, this alignment will be effective only if the magnetic field energy d square by 8 pi is larger than the thermal energy of the region. Even if magnetic field is present and thermal energy is more, it will disturb this region. So, you see such regions?
That's where we are comparing the magnetic fields and turbulence. So in the regions where magnetic fields are doing nicely, like they are aligning grains and doing a spinning coloration.
Doesn't represent thermal energy. It's represent the
No, mostly non-thermal we are getting from our observation.
So that the alignment is perfectly aligned along to the radiation, perpendicular to their radiation direction, right?
This one.
Yeah. All the host stars.
Mhm.
So because of the magnetic field or because of the radiation?
Magnetic fields are frozen in the material, and the material is being pushed by the radiation pressure from the star. So they're just trailing the shape of the cloud.
What is the dominant alignment?
That's where I showed that figure. You remember? Okay, just a moment. This one. You can see it. So in here, turbulence is dominant, but mostly magnetic fields are dominant.
Okay, so if there are no more questions. Let's thank Archana for very good talk. Now we have the next speaker, Sadhana Singh, giving her talk on investigation of dust properties using polarimeter.
Good afternoon, everyone. I am Sadhana Singh. Today I will be presenting. Today I will be presenting my work on investigation of dust properties using polarimetry, in which we have used the So the light component, which is parallel and perpendicular to the short axis of the grain, will face different cross-section area and hence also different extension efficiency, and that's why we will get here the polarized light. So this is the mechanism, or this is the picture which arises how we will get the interstellar medium polarization. And so the overall we can say that the dichoric extension of starlight by aligned asymmetric dust grain which are present in the ISM is the main source for the ISM polarization. So the information which we can extract from the polarimetric observations are these. That is the properties of ISM dust grain, their size, shape and composition, and the geometry of magnetic field in that region, because the dust grains are aligned with respect to the magnetic field, and how is the grain alignment in the region, and what is alignment efficiency in the region, and also foreground dust concentration can also be known with these polarimetric observations. So in this table I have shown all the so we have chosen open star cluster for this study because open star clusters are spread within an area, so the evolution of dust all over the region can be known. So the open star clusters which were studied in previously in past are listed in this table. So these are open star clusters which were studied towards the galactic anticenter direction, means their longitude, means the galactic longitude from 90 to 270 and galactic latitude between plus minus 15. So these are the clusters and their corresponding galactic longitude, and these are the reference. So these are the previously observed open star clusters, and this shows the position of these clusters in the longitude and distance scale. So out of these clusters, these 8 clusters were observed from the Aries using the Ampol instrument. And we have added 4 more open star clusters, NGC 2345, NGC 1817, LAC1 and NGC 7380 towards this direction in order to study dust evolution in that region. So we have observed these clusters using instrument Ampol, Aries imaging polarimeter, which is mounted as a back-end instrument of 104 centimeters Sampurnanand telescope. And we have taken observations at 4 bands, B, V, R, and I, and at 4 positions of half-wave plate 0, 22.5, 45, and 67.5 degree from celestial north-south direction. And for the calibration purpose, means for the instrumental correction, we have also observed unpolarized standard star, and for the position angle correction, we have observed polarized standard star. So basically, we have divided the cluster region into different regions based on the field of view of Ampol, which is 8 arc minute in diameter. And then we have performed observations for each of these regions for in each of 4 bands. And also we have supplemented Gaia data in order to take information of distance, membership, and extension of observed star in this cluster. So data reduction steps have been shown in given such slides, so I'm not giving the details, and also can be found in these papers. So here I am showing the overall results from the open star clusters. So this shows the polarization vector distribution in the galactic anticenter direction. So the length shows the degree of polarization, and reference length for 2% polarization is shown here. So these shows that the orientation of dust grains is parallel to the galactic magnetic field, and field lines follow the galactic spiral arms. There are some regions where field lines doesn't seem to follow general orientation of galactic magnetic field, which may be due to the local magnetic field of the region. Here, the red vector shows the polarization vector for open star clusters, which in detail can be found here. These for the individual clusters. We have shown the polarization vectors plot. So this in all the plots, this dotted line shows the projection of orientation of galactic magnetic field at that particular region. So in this these clusters, in most of these clusters, we have found that the alignment is close to the galactic magnetic field. While there are a few clusters where a smaller deviation from galactic parallel is noticed, for example, NGC 1817, So these alignment, this non-alignment, sorry, the difference in the alignment from the galactic magnetic field shows that the polarization vector shows that the dust has been perturbed at that place, and it has not found enough time to relax and further orient the dust grains towards that galactic magnetic field direction. And coming to the other information which we can extract using the polarimetric study is the foreground dust concentration. So the degree of polarization as a function of distance indicates the presence of dust layers in front of the clusters. So if dust is normally located in layers, and so if starlight encounters at a dust layer at a particular distance, then the polarization will show a small increase at that particular distance. And as all type of dust grains contribute to extension, so the occurrence of dust layer can also be inferred with the extension versus distance plot. So here in the case of cluster NGC 2345, we have found that near the distance of 1.2 kpc, there were a small increase in the polarization, as that is also reflected in the extension versus distance plot also. This for the cluster, for example, for the cluster NGC 1893, they have shown that there existed two different population of dust, and based on this plot, they have shown that there is different rate of polarization for these two different type of different population of dust grains in front of this cluster. So these are the information that how many dust layers and at what distances these dust layers are found in different line of sight. So for the three clusters, dust layer information was not available. So we have taken the data from Helios around this region, and then we have plotted, and then we found a rough estimate of dust layer and we have listed these in here. So, and for the cluster LAC1 and NGC 1817, no indication for the presence of any major dust layer was found. So if we see the overall distribution of dust layers towards this cluster, then we can say that clusters which are located near the galactic plane have shown indication for at least one dust layer, while the clusters which are located below the galactic plane, that there we have not found any major dust layer. For example, LAC1 and NGC 1817, their galactic latitude is around -13. So the other information which we are extracting is the size distribution of dust grain. So Sarkowski in 1975 had given an empirical relation, which is the wavelength dependence of ISM polarization, and it follows an empirical relation is this, where P lambda is the polarization at wavelength lambda, P max is maximum polarization, and lambda max is the wavelength corresponding to which we are getting maximum polarization. So we have taken data in 4 bands. So we have used this relation and fitted this relation and found the value of P max and lambda max for all the stars. And also this relation also shows differentiate between the interstellar polarization and intrinsic polarization, because if the relation fits well, then we can say that the polarization which we are getting is due to the ISM, and if there is a deviation from this relation, then that shows that there may be presence of intrinsic polarization component also. So in all the clusters, it was found that the polarization is due to the ISM, and we have then for all the clusters, we have for 4 clusters, we have calculated the average value of lambda max and P max, and the other clusters, we have taken the value from their respective papers. And the value of lambda max for the general, it was found in previous studies that the value of lambda max for the general ISM lies near 0.55 micron. So the nearby values of lambda max for all the clusters shows that the average size and distribution of dust grains in front of these clusters is similar to the general ISM. And the value of lambda max corresponds to the grain size of 0.15 micron. And also in Witted 1977, they have given a relation how lambda max varies with the galactic longitude. So we have found that based on their relation that the lambda max for these clusters should be range from 0.51 to 0.57 micron, which is similar to our observations also. And we have found this relation which exists by using these observations. Now coming to the polarizing efficiency. So polarizing efficiency is the polarization which is produced from a given amount of extension. So polarizing efficiency is measured by the Pmax by AB. So for the Heltner in 1956 has given this relation that Pmax should be less than 3 RV. This is the limit on the polarization, upper limit on polarization. So we have plotted here. I have shown the plot polarizing efficiency plot for the cluster NGC 2345. So we have seen that all the clusters, and in all the clusters which have been observed, it was found that all the stars were lies below the maximum efficiency line, and these are which are above the efficiency line, these are found to be intrinsically polarized stars. And the average efficiency was given by Fosalva, and in all the clusters, it was found that the polarizing efficiency is close to the average efficiency for our galaxy. And in many studies, it was found that polarizing efficiency with extension follows in power law relation, which is given by this. So we have fitted this relation for the cluster NGC 2345 and found the power law slope as minus 0.67. So a higher value of slope shows that the lesser grain alignment efficiency at that particular region. So here I have here it is an insight into the alignment mechanism. So the increase of polarizing efficiency towards the center and the decrease of lambda max towards the center shows that the local radiation field has been increased within the cluster towards the cluster 4, and that increases the alignment efficiency of smaller grains. And the same as found in this, that with the increase of polarizing efficiency or alignment efficiency, the lambda max decreases. That shows that when there is more alignment efficiency, that will also align the smaller grains, and that will then the average value of lambda max or the average size of dust grain will shift towards the smaller size. So that's why we are getting this. So these results could be results could be due to the radiative, so that there may be the radiative torque alignment of dust grains in that particular region. Here I have shown the lambda max versus AV plot for these clusters which were observed from here. And also we can use Stokes plane analysis in order to get membership identification and evolution of interstellar environment. And also we can determine the membership probability of members stars in this using the Stokes plane analysis. So these for the cluster LAC1 I have performed the members identification, and for NGC 1817 we have found two different population of stars which show different polarimetric characteristics. And for NGC 2345, we have calculated the membership probability of members star using the polarimetric technique. So here is the summary. That is a larger value of degree of polarization is found near the galactic disk, which decreases while going away from the galactic plane, and the position angle is distributed along the galactic magnetic field, and there are some local regions where the different position angle is seen. And those we have found the indication of dust layer in front of those clusters which are located in the galactic disk, while those clusters which are below the galactic plane we have found, or away the galactic plane, we have not found any major dust layer. And the average distribution of size towards the of the dust grains lying in front of these clusters were found to similar to the those that for generalization, that is the lambda max correspond to 0.55 micron. And here I have presented these results from these papers. So, yeah, and thank you for giving me the opportunity.
Thank you, Satya. Thanks so much. Any questions?
Hi, Satya. Okay, just to let you know that red is everywhere. You said that whatever difference you are getting going towards the star cluster, inside the star cluster, that may be due to red. I mean, that is true, but red is everywhere. So whatever coloration you're getting anywhere in the cluster is due to that. Okay, my question is, especially in these clusters, it is sometimes hard to deal with the crowdiness of these clusters. So how do you take care of any overlapping or crowdiness in the coloration observations?
Okay, first of all, these clusters were in the core of these clusters were not so much crowded. So, and in the observation, we have manually selected the G stars. So there should be no overlapping of O and E ray of neighbor G stars. So we have done manual selection, and then we have also checked that there should be no overlapping. And also we have in the reduction procedure, we have plotted the polarization. We have calculated polarization at different apertures. So means the aperture size. So we have plotted, and then by the plot we have seen that where the this is like the curve of growth. So where the polarization gets constant, we have taken that aperture because there were some stars in which the curve like this first constant and then goes increasing. So that's so that after that aperture, this there may be some overlapping. So that's why that increases.
I have few more points, but we can discuss later because others may have.
Okay.
You talked about this dust alignment. So for alignment of the dust, so you talked about dust alignment. For the alignment of the dust in the magnetic field, the dust should have intrinsic or induced magnetic dipole. So what mechanism you think, whether it is intrinsic, if it is induced, what induces this magnetic dipole in the planes?
Means how the dust and dust
See, simple. Dust grain, if you consider silicate grains, if you consider dielectric, they don't have magnetic moment, right?
Yes.
So it should be induced. So what mechanism induce this dipole moment? Otherwise they won't align.
Yes. Actually, I've seen that. Not I will read that Barnard effect. How the dust means the paramagnetic grains, how they are linked with the means magnetic field. So that Barnard effect causes the alignment of dust grains. The spin axis with the magnetic field.
No, but still there should be some mechanism. Paramagnetic or dielectric material, they don't have permanent dipole. Magnetic.
Yes. So
It cannot be ferromagnetic. Iron is almost not.
Or silicate like
Either silicate or carbonaceous. Carbon.
The alignment in. So okay, so
Okay,
it is
we can discuss later on.
okay.
There is one short question. See, you showed this table in different clusters. In different clusters, this lambda max is different, right? 0.51 micron to 0.59 micron, right?
Yes.
And this lambda max is a proxy for the size of the dust grain.
Yes.
You said more or less the dust size is same. It will be different, right? See, if it is 0.59, the dust size should be larger. If 0.51 is the lambda max, it should be smaller compared to this.
Yes, relatively, but
But that
not
you saw that in the last graph,
in the
that we can show that we have shown the variation of the lambda max. So where you saw them that lambda max variation. Yeah.
So more or less similar.
Usually the earlier results show that they follow in that direction. And for discussion purpose, now you are talking of layers. Did you try to look CO map? Because then you can find that clouds are there. So maybe that could be just look at the CO map. And then if you have two layers, you can confirm. Your data doesn't confirm that you have two layers. It's just indication.
Yeah, actually for the dust, you don't have to go to the CO, but you can have even
It's
blank data
dust is
itself.
always one data is loud, right? It's 1% dust in a cloud. So always CO is there, dust will be there.
Yeah, so flag, I think
It's not that way.
You can check the flag all sky map as well as Dame's CO all sky maps. So just you can check this.
Yeah, let's thank Sadhana and let's move on to the next speaker, Namita, for polarization observations of open cluster using.
Hello everyone, I am Namita Optical from PRL, and today I'll be discussing about the polarization observation of the open cluster using 1 meter class telescopes. So using mainly AIM-POL. So I'll start, and this is the outline of my talk. So I'll start with the basic introduction of ISM polarization. Then what motivates us to start this project? And with that, I will proceed with the observation, data reduction analysis, and with some initial result that we have obtained. So to start with the historical perspective, that in the earlier 20th century, it was thought that the dark region in the skies are holes in the cosmos, or there are voids of the voids in the star distribution. But today we know that this is not the case. The space between stars is not empty, but it is filled with the interstellar medium. And the submicron-sized solid particles, which are known as the interstellar dust particles, they account for only 1% mass of the ISM, but they play a very important role in the galaxy evolution. And these dust particles, they can interact with the starlight, they scatter, absorb, and re-radiate the starlight. And they have a huge influence on our view of the universe. Also, the obscuring effect of this dust particle, they hinder in the determination of the stellar distances, which are very important for the galaxy structure studies. So this is all about the interstellar dust, how their obscuring effect change our view of the galaxy. And apart from this extinction, in 1949, Holland Hitler observed the starlight polarization. Soon it was realized that there is some link between the extinction as well as the polarization. For example, the bottom panel map shows that this is a polarization map of more than 5,000 stars distributed in the galactic plane. Here the vector, length of each vector is correspond to the degree of polarization, and the orientation is correspond to the polarization angle. By comparing, so by comparing the first and second, we can easily see that the regions which are highly obscured shows large polarization. So there is definitely some correlation with the extinction and the polarization. So it was confirmed that the medium which is responsible for the extinction is the same medium which is responsible for the polarization. So this explains the ISM origin of this polarization. And how now, how the polarization starlight is getting polarized. This is very well explained by Sadhana and yesterday by Maheshwar sir. So probably I will skip this slide. And I wanted to emphasize that from the polarization, we can measure the direction of at least direction of magnetic field, which is today explained by the Asnadi. So this magnetic field information can be obtained from the polarization studies. And what else we can do? The grain properties. As explained by Sadhana, that we can also study the grain properties, the size, we can constrain the size, the composition of the dust grains present in the ISM using the polarization. But my emphasis is that we can also study the dust distribution along the line of sight. For example, from this cartoon diagram, here, the first star, there is only one foreground dust layer. And for the second, this star, there are two foreground dust layers. So the starlight will be passed through this two foreground dust layer. Now, if the dust grains are oriented, the dust grains of the two clouds are oriented in the same direction, then the polarization, degree of polarization of second star will be more than as compared to the first star. But if the orientation is orientation has some deviation, then there will be a decrease in the polarization. Whatever be the case, we will see a jump in the polarization, whether increasing or decreasing. So with this motivation, that we in this way we can give the distance, or we can find the distance of this dust clouds present along the line of sight. because now the structure of, I want to here emphasize that the structure of Milky Way galaxy is not known till now. So how many spiral arms are there? This is not very well known, but dust is distributed in the spiral arm. Now to study these spiral structures, we need to know the distance, or we need to know the distribution of these dust clouds. So for that, we need to know the distance. So the polarization will combine polarization information with the distance information, which is very accurately given by Gaia. So by combining these two information, we can find the dust distribution along the line of sight. For this purpose, we have chosen galactic open cluster. Why open cluster? Because open clusters are present at the same location and have similar distances. So we can constrain the distance very well as compared to the randomly selected any individual stars. So with this, we wanted to study this this distribution. This plot shows the distribution of a galactic open cluster presented in Gaia DR2 data. So different colors represent the presence in different galactic quadrant, and the circular features are spiral arms, the known spiral arms, and so we wanted to study open cluster in different. We wanted to study the polarizations of open cluster in different line of sight. For example, here I have shown three line of sight, but in one line of sight, we wanted to cover different cluster present at different distances, so that we can show that there is a dust distribution along similar line of sight. So with this motivation and this aim, we started observation with our 1.2 meter telescope at PRL. And we have our in-house built EMCCD based polarimeter. It is an imaging polarimeter. The first image is the polarimeter at the back end of the 1.2 meter telescope, and this image shows the optical layout of the polarimeter. Here we have a Glenn prism, and then a rotating half-wave plate which is attached to a stepper motor. So it covers 7.5 degree in each step. So it covers 48 angles in one rotation. And then we have placed one fixed half-wave plate. After that, there is a wire grid polarizer which acts as analyzer. And then after filter field assembly, the light will finally detected as at the EMCCD. So with this, we get the field of view of 3 arc-minute. And using this telescope and the instrument, we targeted one cluster, CZ3. It is at 4.4 kiloparsec according to Gaia DR2. So this is a distant cluster. We have chosen this distant cluster in order to see the number of dust clouds present foreground to it. So these are the basic parameters: the location, distance, and the age of this cluster. And the left image shows the DSS image of this field, the core center part of this field. And we have observed 43 cluster in these 3 arc-minute, one pointing of in EM pole. And here it is the right panel shows the vector polarization vector diagram. Here the horizontal line is a constant latitude line, means the orientation of the galactic plane towards this direction. Here we can see that the polarization vectors are not parallel to the galactic plane. This is one thing. Next, we wanted to check if there is a dust clouds. There is a different dust cloud present foreground to the cluster. Then this could happen. The polarization finally, because it is a cumulative effect, final polarization angle could be different from what we expect as a parallel to the galactic plane. So to do this, we have cross-matched our catalog with the distance catalog given by Baylor-Jones 2021. It is based on the Gaia EDR3 data. And we have plotted the degree of polarization angle, and the extinction as a function of distance. So in this plot, we can see there is a 2 jump in the polarization as well as extinction. At least 2 jump are present. So because there is a very less data present here between it, so we cannot give an exact distance of the cloud that is foreground to the cluster. But we have given the upper limit that the cloud should be present at a distance less than 1.2 kiloparsec. And second cluster is closer to the cluster. Second cloud is closer to the cluster, which is at 3.4 kiloparsec.
And by checking the Lind's dark cloud, we have found that LDN 1306 is present at, towards this location at 1 kiloparsec. So probably this first is cloud which is we have detected from the polarization observation. This probably is a LDN 1306, and second cloud is closer to the cluster. So as a result, we have detected two dust layers foreground to this cluster. And we have also confirmed the distance of these two clouds from the molecular data, CO data. And we have found the kinematic distance of the molecular data, which are coinciding with the what we have predicted from the polarization and extinction. Now we wanted to do this kind of work towards a different line of sight, but the hindrance is that, sorry, before that we also, what we did, we combined this our result with the already available cluster members. Already available clusters. So there are 5 clusters that are available in the literature for which polarization is there, and all these clusters also are observed from the aim pole, and these are present. This plot shows their location in the galactocentric coordinates, and these are present along the same line of sight but at a different distances. So this right side plot shows the degree of polarization for different cluster as well as halos from halos in gray color as a function of distance. So here we can see that the polarization is increasing uniformly up to 1 kiloparsec. This explains the dust is distributed uniformly in the solar neighborhood. But at 1 kiloparsec, we see an abrupt increase in the polarization. And here this dotted line shows 1 kiloparsec and 2 kiloparsec lines. Here one thing to notice is that this polarization just before and after the gap is almost same in this region. And this could means that there is less dust content are present between this gap, which is polarizing the star's background to it. And also the individual stars towards each cluster are less in this gap. To verify it more strongly, we have checked the 2 mass high quality sources to see whether there is a decrease in the number density. So we have found a decrease in the number density between this 1 to 2 kiloparsec gap. So there is a decrease in number. There is a decrease in number density as well as decrease in number density as well as dust density. So this could mean that there is an interarm region between the local and Perseus arm. Now this kind of study we wanted to do in different line of sight. So we require large sample set to be covered, but our EM pole field of view is 3 arc-minute only, and large cluster require large number of pointings. So we make use of Aries imaging polarimeter as a back-end instrument at the Sampurnanand telescope. And the main difference between the EM pole and AM pole is that one EM pole was 1-channel polarimeter and it is dual channel polarimeter. And in Mars, we have observed 3 clusters at towards similar line of sight, but at different distances. And then in the meantime, we have developed a pipeline for the basic data reduction of the AM pole data. And this is a Python-based pipeline and it is fully automated. So what the pipeline will perform, it will do the general task like bias subtraction, shift and stacking. Then astrometry is done by astrometry.net. Then the main thing is that this is the DSS image of the cluster BE69, and this is what we have observed from the aim pole. For each single star, we are getting 2 images corresponding to E-ray and O-ray. So the first and foremost thing is to separate this E-ray and O-ray. So our code will, so because as Mahesh sir said yesterday that the difference or the shift between the E-ray and O-ray is fixed. So the code will ask for a pair for a rough position of a pair of E-ray and O-ray component. Then according to that, it will calculate the shift and apply to all the stars. In this way, it will disentangle the E-ray and O-ray component. After doing it, that again task is the photometry. But the problem with photometry, we have used aperture photometry. The problem with photometry is that crowdedness of the field. So there could be some stars, close by stars, where aperture could overlap, and there is again overlapping problem it increases because of the part of E ray sources are overlap with the O ray sources and vice versa. So to resolve this issue, what we are doing, what our code is doing, it will first collect the this is concentric circle correspond to, for example, 3-time FWHM, 2-time FWHM, and 1-time FWHM aperture. Now these what will happen? It will take 3-time FWHM. If it is overlapping in 3-time FWHM, then it will discard that aperture and start looking for the flux in 2-time FWHM. If it is still overlapping in 2-time, then it will come down to 1-time FWHM. If still it is overlapping, then we have flagged that source and we have not used those sources in our further analysis. In this way, this was just an example. We have taken 12 to 15 apertures between 1-time to 3-time FWHM, and according to that, what Sadhana explained, according to that, we have fitted the polarization by using this modulation relation. And this is the example of one of the standard star, how the modulation is fitted. So from this, we can find the polarization and polarization angle. So we have reduced the two cluster data from this. This is the result from one of the cluster. So first one is the vector polarization vector. Here the solid line represents the orientation of galactic plane. Most of the stars are oriented in the same direction, which can also be seen from the middle panel, which is the distribution of stars in peak theta plane. And finally, what our purpose was to see the dust distribution. Now here from this third one, right plot, it is can be seen that the degree of polarization and the polarization angle is changing at 2 positions, showing a jump at 2 positions. Overall, it is polarization is increasing and the angle is remaining constant, approximately constant, but the dispersion reduces with increase in the distance. So, and we are seeing that there could be probably there are presence of 2 dust layers, and we will confirm with the other archival data also. These are just preliminary results, and we are combined again with the different cluster available in this direction. And this is the result. More or less towards this direction, towards the galactic anti-center direction, the dust is distributed uniformly. For example, from the upper panel of first left image, it is distributed uniformly, and the polarization angle is also somewhat constant. And this plot shows the average polarization of the cluster members. The colored points represent the average polarization of the cluster member. So up to 2.5 kiloparsec, it is seen that the polarization is increasing uniformly. And after 3 kiloparsec, there is a decrease in the polarization angle as well as the degree of polarization. So it may happen that the distant cluster get depolarized due to the different dust layers present along the line of sight. So to summarize, I wanted to highlight the last 2 points, that the polarization observation of distant cluster require long exposure and clear night. So we require a dedicated telescope time to explore the dust distribution in the galactic plane. So with this, I wanted to thank my supervisor, Dr. Shashikiran Ganesh, and my collaborators. And thank you all.
Yeah, you told about selecting the apertures, right? Different 1, 2, 3.
Yes, yes.
So you are doing aperture photometry. Why not PSL?
I started with aperture photometry. Now I'm doing a PSL.
Yeah.
I will compare the result and
I think PSL will be more suitable.
Can I ask one clarification very quick? Your second or third slide where you were showing the import field or import field.
This
No,
is
next one. Next.
This is
Yeah.
EM pole.
So it seems like this bigger star is saturated or not?
This star could be is saturated. We have not used.
But you have a reduction there. How did you do that?
Sorry, what there?
But you have a red
You have
line
just-
segment there.
We have not used in the analysis part.
You're still showing it.
Oh, yeah, I forgot to change the image, but please remove.
Yeah, let's thank all the speakers of this session and thank Namita especially. So we'll leave it back to.
Yeah. So I think, thank you all. We are progressing very well. And before we break for the tea, there are 2 quick announcements. First one is for the conference dinner. Vehicles will start from this place at 6:30 p.m. today. So we have got to assemble here. That is one. Second announcement is actually we need users' feedback. and we are circulating over email one Google form. And it is very important to collect your inputs. Of course, when you feel like we are not asking you to propose new instruments, but at least any input which can improve and help us in discussion the future instrumentation. That is the last session of this workshop. That will be very helpful. Please do that if you can do that by today or tomorrow morning. Thank you very much.
Analog.
अभी है एक मिनट वेट कर
टेक्स्ट मैसेज दिए
इसका
उसका ऑडियो भी है, ऑडियो भी है उसमें।
हाँ तो अभी आए हैं ना।
So welcome to the last session of the day. We have 4 talks lined up for you. The general theme is variability, usually. And the first speaker is Santosh. We'll speak on the Nainital-Cape Survey and some aspects of it. So Santosh.
By the way, before that, we have to.
I will do that after his talk.
Okay, after it.
Okay, sir, thank you very much. So you have already heard about the Nainital-Cape Survey on many occasions. Since yesterday by Professor Sita. So today I am going to tell about the results obtained after 2000, because yesterday basically she focused yesterday on the wet campaign that they took from 90s to 2000, and then we started this Nainital-Cape Survey. Then I have used the title Utilization of the Moon Observing Period, because most of time observers generally prefer the dark period or gray period. Fighting always starts with the dark period. We want dark period, we want a gray period. So who will utilize the moon period? So keeping in mind that there is a lot of competition for the dark and gray period, we thought to start a survey project in moon period, because our for the survey we took the sample. Most of those stars are bright stars, and for their photon noise was not the problem. And they were classified spectroscopically because they are bright and the spectrum were taken easily. So
Okay, sir. Clash.
Yeah. So there are some missing photo here. So these are our project investigators. So here Ramsagar's photo is missing anyway. So Peter Martinez and Dr. Sita, SK Gupta, US Survey. So these are the investigators of the projects. And here Sita already displayed yesterday this picture. So myself, Davanpur, Ashoka, and Girish. Actually, these 4 are the responsible for the observation from Nainital and Cape Town, Sutherland. So these investigators are really thankful for starting this Nainital-Cape Survey, this legacy project. So the objective of this survey project was to search and study the pulsation in chemically peculiar star using the fast photometry. And if you find some interesting pulsating stars, then derive their basic parameters and chemical composition using high-resolution spectroscopy and spectropolarimetry. And then apply the asteroseismic technique to study their internal structure and evolution. You know, in what stage of evolution they are. And then to develop state-of-art backend instruments for the highly precise multi-band photometry and high-resolution spectroscopy. So this was the one of the other aim before the start of this project. So astroseismology, basically nothing, just to study the stellar interiors using the waves, and basically the waves are either P modes, where the pressure is the this restoring force, or G modes, where the gravity is the restoring force in case of the white dwarfs. And then to analyze the stellar oscillation to study in stellar interior, because different modes penetrate to different depth. So if we detect the different frequency mode, then because they go the different part of the stellar interior, so we can have the whole information on the whole interior of the star. So in order to have the astroseismic techniques, then what type of techniques we should have for the astroseismology. So basically three main observational techniques are used. One is a photometry that can be done from either ground and space, particularly after the launch of the Kepler and TESS. People have been using high-resolution spectroscopy to determine the basic parameters, because for modeling, the basic parameters are highly required. Not only basic parameters, precise basic parameters are very useful. And then interferometry to determine the radius. Basically, people use to determine such parameters using the interferometry. So primary aim is to extract the frequency, amplitude, and phase of the waves. Those originated at the stellar surface with very high precision. And in spectroscopy, the precision in the measurement of the radial velocity is of the order of tens of second per centimeter per second. So in order to have such level of the precision, we need very high stable spectrograms, because their amplitude of oscillation is very small. So to minimize the scintillation noise and have long duration observation, astronomers prefer to use space missions that provide this ppm order, part per million order of precision, and that is very important for such astroseismic study. So just what is the application of astroseismology? Here I have depicted. So if we know the this dense spectrum, and if we can measure the large frequency separation and low frequency separation, then the large frequency separation scales with the average density of the star. Then we can determine the mass of the star. We can determine the density. And the small frequency separation is sensitive to the interior gradients and the epoxy of the age of the star. So we can determine the basic parameter mass and density as well as age. That is the only way to determine the basic parameter independently. Another method. So the age can be determined, you can see here. So just we plot between the small frequency separation and large frequency separation, and this is a theoretical diagram you can see. So we place the star where if we can determine precisely the large frequency separation and small frequency, we can estimate the age of the star precisely. So this is the one of the direct way to determine the basic parameter. So we wrote a review article for the astroseismology of pulsating stars. Actually, that was the part of the Indo-UK conference that was held at this place in 2015. So all the methods and results have been briefly highlighted here. So astroseismic tools, you can see that the HR diagram, various type of the pulsating stars are populated here. We can see the delta Scuti stars, we can see the rapidly oscillating star, Mira star. So according to their pulsation period, we can see different type of the stars in the HR diagram. You can see the white dwarfs sequence as well. So basically, Dr. Sita and their group, they were studying these white dwarfs from Nainital 1 meter telescope. But we were focusing on the delta Scuti and rapidly oscillating AP stars from this under this Nainital-Cape Survey. because the pulsation amplitude was very small. For that, we need very high precise photometer where the sky condition is excellent. So that is only possible to obtain at Nainital during those time. So people have been using this telescope for the high precision photometry as well. So for the rapidly oscillating stars, so these stars were discovered by the Don Kurze and group from South African Astronomical Observatory. So these are the pulsating non-radial variable stars of spectral type A12. They are cool, they are magnetic, their magnetic field is of the kilo-Gauss order. So their period is very small, of 5 to 23 minutes, and amplitude of variation is of very small millimagnitude amplitude. So for that, this site is excellent for the study of such type of stars. And they pulsate in the high overtones, equal to more than 30, and they are low degree, because in photometry it's very difficult to detect the high degree modes, right? So when we started this survey, at that time only 28 stars were from the southern hemisphere, and 3 were from the northern hemisphere. So as Dr. Sita already told that to why what is this bias, so then we started this survey. So the science drivers were basically what are the cause of the specularity in these stars, why they should not pulsate, and because the chemically peculiarity is due to the radiative diffusion, the heavy elements sink toward the center and the light elements to move to the surface. So we see the overabundances. So then to determine their basic fundamental parameters, as I already discussed, and from the measurement of these fundamental parameters, we can study their stellar interior, inversely state as various states, and magnetic field topology, pulsation, excitation, all these area we can study. So for the survey, a photometer was developed, because for the survey, this fast photometry was chosen. So this photometer was developed at ISRO and in the collaboration of ISRO and ARIES, I would say. So a proposal was submitted to DST, costing 10 lakhs. And Professor, I assume that Professor Dr. S.K. Gupta was the PI, if I see, and I think S.P. Singh was the co-investigator. Yes. And because yesterday people were discussing about the money, so this 10 lakhs at that time was very good amount of money, 10 lakhs. So then good thing is that you can see here P. Sri Kumar. So I think you joined at that time ISRO, right? Or at similar time, I don't know. But he helped a lot. He supported this project. And even I was visiting there. So we have assembled the components over there. But he was very friendly. Really, thank you, Sri Kumarji. So he supported a lot, because all the components were bought from the ARIES, all the assembly, testing, and all was the responsibility of ISRO. So, so this photometer was developed at ISRO laboratory, and Sita really acknowledgeable for this development of this photometer. So these 1 meter telescope was used for the survey purpose, and at Nainital, and this 0.5 meter telescope at South African Astronomical Observatory at Sutherland. So later, as I said, that the basic parameters are important for the detailed study. So we use 2 meter SCT and 6 meter this special astronomical observatory telescope. So we use also the Mercator 1.2 meter telescope. So then we also use this Kepler telescope, and recently we have been using this test mission as well for our study. So this is some old photographs. So what we have been doing in the daytime, we have been doing all the preparation, because at that time there was not much store. So we have been taking all our staff, means our friends, I would say, Jeev and Ramakant. So we have been going, because we have to change the instrument. So generally CCD was there. It's difficult to change such instrument by a single person. So we all used to go there and then change the instrument, and then start for the evening observation, right? So then, because as I told you that we have been using the moon period observation. So during the full moon period, mostly we conducted this Nainital-Cape Survey. And because the light curves were real time display, so we have been getting the data, analyzing parallelly, then again see if there any variation, then again monitor it for a long time. So in the night itself, we can get the results. Right? So when the first, okay, I will come later. So anyway, this is these were different surveys I have listed here. So so Don Kurz, he started the survey in 1982, and where he investigated 5 AP stars from southern hemisphere. And in 12, you can see the Nainital-Cape Survey. We investigated more than 350 stars from our the survey. That makes it the longest survey ever taken from the ground in terms of the time spans. You can see the various samples. So these are the this is the statistics of the different surveys. 1, 2, 3, all these surveys. So you can see in our survey 12 number, we got the 8 positive results, and 12 positive results were obtained under the Cape Survey. That was initiated by Peter Martel and Don Kurz from the South Africa itself. Because only that time the survey were taken from the South Africa, so most of the stars were discovered from the southern hemisphere only. So, so total duration 25 years, and the AP and the sample stars were selected from the catalog of CP stars. And this because this is unique, because the survey was conducted from both the hemisphere. People have been either using such type of survey either from northern and southern, but we use both the telescope in the both the hemisphere. So I have observed more than 350 nights. So because sometimes the half of night were used and the clouds came, so night quality was not good. So a lot of nights were observed. So the positive detection was 8, where we discovered 1 rapidly oscillating stars and 7 delta scuti stars. So this is the my PhD thesis. So where we discovered the so many delta scuti stars. So so we also use this spectrograph here, OMR spectrograph for the spectroscopy. You can see. So both the photometry and spectroscopy was used for from this telescope for our study. So this was one of the chapter in Astrophysics Space Science Library 13, a part of the super light curve showing the level of precision that can be obtained from a ground-based telescope from a good side. So you can see the what type of the quality of the light curve we have obtained from 1 meter. So this has already talked about the precision from the CETA. So the left is the sky transparency, where we cannot control. So the only can be control means where we can observe from the good side. So that can be minimized. So these high-resolution spectroscopy were used to determine the basic parameter. Also, we have used the spectropolarimeter to detect the magnetic field in these. But till now, we did not find a magnetic field in any of the candidates. So this is the PhD thesis of Greece. So this was the first rapidly oscillating AP stars discovered by Greece, and yesterday Shita have already talked about it. So this one of the thesis was by Sukanto Dev. So he worked with SP Singh. So he found the period of in one of the stars. So he found the, you can see the signal, the noise level, how noise level we have achieved. So not only his students also got the similar results. So this is very important. So this is the PhD thesis of Chavi. So she also did the spectroscopic analysis as well as photometric. So the stratification, she worked on the stratification of magnesium, different of elements in atmosphere of the stars. So she found that the stratification of the magnesium silicons. So some of them are abundant in the outer layer and abundant in the deeper layer. So this work was also very remarkable. So this work was done by Sanjeev Kumar Tiwari in PhD thesis, where he studies various type of the many pulsating variables he studied. So this also we developed one CCD based photometer on 1.02 meter. So this telescope we used, and these are some specification of this telescope. We characterize this CCD, and one of the light curve from this telescope observed from this telescope is TRASH 3, and that was published in Manora Peak 2020. So then the space photometry came into the picture, from where this sky transparency also can be overcome. So this we have been using the space photometry. So this is the one of the stars we recently discovered, that is called the heartbeat stars. So this light coverage is resembled to the ECG type of. So you can see that two stars are coming together and the intensity is increasing. And when they are going to apart from each other, they are in this intensity decreasing. So that we can study in such type of system the tidal disruption, how the tidal disruption takes role. So now two PhD students are working in this field. Both of them are the externally funded, Manora Sarkar and Atul Dilip. So they are working hard to perform the astroseismology of the CP stars and continue this legacy survey. So now this is the collaboration of the astroseismology now. So our collaboration is extended in many countries. So we have been working together. So recently one student did PhD under us in this evaluation of the origin of the chemical anomalogy in AM stars. So this PhD was under this Indo-Belgium project. So now what are the future prospects? So because you see, this is the 1.2 meter Mercator telescope where the Hermes is equipped. And in this, with this spectrograph, on an average, 30 papers are coming per year, 30 papers. So one of my suggestion or recommendation or request, I would say that it would be nice if we can have some high resolution spectrograph on 1 and 1.3 meter telescope, so that we can use the moon period in better way. So this is one of my proposal. So these are the international bilateral project originated from this Nainital-Cape Survey, I would say. So had the Nainital-Cape Survey not in the existence, I don't think that, because then I would say that this is the origin of this Nainital-Cape Survey. So this was the one of the international workshop held in 2005 at Nainital. So where we discovered the missing mode here. So Indo-South African workshop was also organized at Nainital. So this is a group photograph. So this was the first Bina workshop held at Nainital in 2016. Instrumentation science with 3.6 meter telescope. This is the second Bina workshop that was held in Belgium. So you could recognize many faces. So the third Bina workshop is scheduled in March 22-24. Thank you, Dr. Shah. 23. So yes, yeah. So this is the. I thought that this is the best platform to advertise this workshop. So I would say ISRO photometer was mounted in 1997, and in 2020 we published this paper with many collaborators. So almost 25 years have completed of this Nainital-Cape Survey. So we are also celebrating 25 years of Nainital-Cape Survey over the golden jubilee of 1.02, 1.04 meter telescope. Thank you to all my collaborators. Professor Ramkaga, thank you very much for your support.
Any comments, questions? Yeah,
it was an excellent example of what can be achieved, what kind of precision can be achieved with telescope. You mentioned that the chemical peculiar part comes because of the magnetic fields.
I have not said that
You said
because there are two type of peculiar star. One is the magnetic, other is the non-magnetic.
Oh.
Chemical peculiarity is coming due to its intrinsic property, diffusion. That is called the diffusion. The heavy element sinks to the center because they are noble gas kind of structure. Those who have noble sense, because they are not supported by the this photon, whatever the radiation comes. And the light elements, they move to the surface and they become the overabundant.
Yeah, my question is
but the magnetic field is sometimes somewhat responsible for the chemical peculiarity, because they rotate slowly to the stars, because the slow rotation is required for the chemically peculiarity. If there is no slow rotation, other these elements will mix up. Okay. So either binarity or the magnetic field. So though both of them are the responsible.
But you have not detected magnetic field.
Yes, that's right. So where we have not detected the magnetic, in those cases that they are the binary system. In the binary system, the tidal force slow down. Yes.
Turning.
Yes.
Is expected.
But other authors have discovered magnetic.
Sorry.
Other authors have
of course.
measured
Yes.
What is the magnetic field?
Magnetic field means it's as I told you that in AM stars metallic stars, there is undetectable magnetic field. We could not detect. In AP star, their magnetic field range I told you up to 30 kilogauss. Yeah, it's high.
Professor Joshi.
A short question.
Yes.
You said you can estimate mass with a single star. What is the accuracy?
Accuracy 20% or so. Yes.
So in case of binary,
Yes, yeah. So, yeah, 10%. In binary, we can determine more.
even in
Okay.
So this administrating, you mentioned, so you are having something like a survey in mind, because HRS is coming on board. That will also serve some purpose, so, I don't know.
Even I proposed long back the CCD photometer, and then Professor Sri Kumar also helped a lot us in pursuing that proposal.
Well,
The
with
quantum
that, we'll
energy
discuss
also
tomorrow, right?
Yeah.
We'll discuss that tomorrow. It is on the agenda.
So I think it will be nice if we can pursue such a project.
Yeah, two quick comments. One is, you mentioned about the, low order mode and the high order mode. So what is the current status of detecting, mode number, higher mode?
I think in the low mode, less than 3 only.
So even with other surveys or
No,
does it exist?
yes.
So you don't have much information about subsurface anyway?
Yeah,
Because
yeah.
low order only penetrates
Low,
to deep,
yes,
but
yes,
the
yes, yeah.
the high orders are restricted to it. So convict, of course, these stars are not all convicted, but you don't have still information
Yes.
exactly.
Yeah.
So, a lot of these magnetic field, understanding will not be, sufficient unless we have higher order L mode
High mode,
observation. So the other comment which I was trying to catch, you mentioned the spectrograph for 1 meter and 1.3 meter.
Yes.
So is the same spectrograph can operate in both this?
I have really not thought about it. Just came in because
I
we
mean,
have
it's a
been, because
completely
we have
different
been, because we have been using hemispheres long many years. So that's why I thought
That could be sort of course, good
Yeah.
thing, but you have to keep it in mind.
Yeah.
If you want to use it in both the.
So then we have to transport it. From
Yeah, that's a
also.
different issue, but mounting itself.
Because I don't Yeah, at the telescope I have seen different focal lengths.
I mean, if you are mentioning something. You passing, you mentioned spectropolarimetry. What is happening with that?
No, so we have used the Russian telescope for the spectropolarimetry.
So you're not planning anything here?
No, not my main, because I do not want to speak many things. I do not want to.
We will discover it.
Dr. Bhattacharya.
basic question on you, this asteroseismology and
Seismology.
Now, apparently these are non-radial pulsation. But what is the physical process for seismic type of activity?
So basically the opacity mechanism is the main kappa mechanism operating in the partial ionization.
But should they give rise to such large scale?
Yes, the opacity drives these pulsations. Because there are some conditions when this
But it has been calculated and finally converted to intensity change.
Yes.
So basically caustic mode.
Yeah, acoustic mode is. Even in white dwarfs and there we have the G mode and gravity mode.
So let's thank Santosh again. Nice talk. We have a video message from Don. You heard a lot about Don. So he was a professor at University of Cape Town and later moved in early 2000 to University of Central Lancashire. I think he's an emeritus professor there now. So I know I used to meet Don every time he used to come to Nainital because he used to stay with me in Delhi. Yes. And extensive lecturing to our students all the time.
Very good speaker.
Yeah.
Renty is in UK.
No, in Cape Town. Okay.
Good day, everyone. I send you best wishes for your golden jubilee of the Sampurnanand telescope. I wish I were there with you to celebrate and to participate in the meeting. Now, I know from the picture behind me, it looks like I'm here in Nainital with you, but I'm not. That's a picture I took on one of my many happy visits previous times. I'm sending this message to you from the Eastern Cape province where I live in South Africa now, a small town called Port Alfred on the Indian Ocean. I first heard of Nainital more than 50 years ago. I started as a PhD student in Texas in 1970. And in 1971, there was an occultation of the bright star Beta Scorpii by Jupiter. And expeditions were sent out to various places in the world from Texas. One of my professors, Brian Warner, and an electronic wizard, whom the older amongst you will still remember, Ed Nather, both came to Nainital to observe the occultation of Beta Scorpii by Jupiter. And of course, I got to hear about all of that in the planning stages. And when they came back, it was the first I'd ever heard of Nainital. For me, growing up in California and then studying in Texas, this was a place far, far away on the other side of the world. But it captured my imagination, and it became a place that I knew that I wanted to go. And then in the early 1990s, I was participating in the Whole Earth Telescope, which was developed and being run from Texas, but with many collaborators around the world, and a team in particular observing from Nainital. And so I was collaborating with and publishing with Krishnan Marar, Sita, who I believe is there today. Hello to you, Sita, if you are, Biana Shoka. And we developed a relationship scientifically and corresponded, and eventually that led to a group of us beginning what became the Nainital-Cape Survey for rapidly oscillating AP stars in the Northern Hemisphere. I was then fortunate enough to come visit Nainital on many occasions, 25 years ago, and then for the following few years, observing with the 1 meter telescope on that project and with many of you. I met there, I think many of you today, I will have met Brijesh, Ramsagar, I think that you were there today participating in this meeting. Santosh, of course, you were a student back then. Sneh, I think you were there. Chobi, and I'm sorry if I'm forgetting some of the others who I met at that time. So my best wishes to you for this celebration of 50 years of your 1 meter telescope. I hope at some time in the future I'll be able to return to Nainital for some other purpose and join you all in some scientific discussions and perhaps even some observing. So have a good meeting and best wishes from me. Bye now.
So we'll send a message to Don.
Yeah, absolutely.
Okay, we move on to the next talk with another important survey, Nainital microlensing survey. Yogesh will talk.
Okay, thank you very much. I'm talking about the Nainital Microlensing Survey program, using through 1 meter telescope. This is long back. I mean, we started this program 25 years back. I will go through all these slides, and because we could not continue this program for a long period of time, it's not just our place. In fact, we tried with the 2 meter Henley telescope also, but the program had to be abandoned. So anyway, I will go through all these things and what we have got during these survey. So motivation to search for microlensing survey. Yeah, that was of course the search for dark matter at that time. Of course, when in many places we were trying to search for dark matter, and what is the contribution of the dark matter is the one of the technique to find the dark matter, this microlensing survey program or even lensing program. So then Ramsagar in some of the meeting went to Paris, and he had some discussion with the French group, and that time they were doing some microlensing program using 1.2 meter MDM telescope in Arizona. So he thought that okay, we can also do this program with our 1 meter telescope. Only thing is that of course these kind of program needed a dedicated time on daily basis. So I will talk again about all these programs. I mean, of course, then he came back and he asked me to, start this program here. Before that, no one have ever tried this one in India. Of course, one of my co-supervisor, Professor Dienerson from TFR, was doing a little bit technical work. That was a gravitational lensing, not microlensing thing. But we started this program here. A difficult journey I had with the limited facility, because when we had started this program, of course, 1 meter telescope, so you cannot go very deep. So you needed a very long exposure time. One limitation. Other limitation was we had only 1K by 1K CCD at that time. We bought the CCD in 1993, and until 1999 we had just 1K by 1K CCD. And field of view of that CCD is about 6.5 by 6.5 ArcNet field. So that was limitation. So if you start this program, you have a very small field of view. I mean, you are monitoring this same field of view for a long period of time. So while the other survey normally these kind of survey do the wide field imaging. So this is the one limitations we had. So anyway, after many years of observation, we could detect one microlensing event from India, and not just one microlensing event from India, but apart from that, we have detected many other kind of variable star, which I will go through. That is called byproduct of this microlensing survey, and what is the future of such survey in India now. Okay, so as I said, it was the motivation from the which we have taken from the French group, and by the time we have started this program, they have moved to 2.5 meter INT, Japanese telescope. It was dedicated time for them on 2.5 meters and with large field of view, and ours was just a small field of view. When we started this program with 1K by 1K CCD, but we have started this, and then in 1999 we got one new CCD, 2K by 2K CCD. So first year of observation was just by small 6 by 6 arcnet field, but later we got 13 by 13 arcnet field. So I'm not going to detail about all these physics of the microlensing thing, but the three important things which I will tell you about this. The microlensing, which you can see the light curve, theoretical light curve of the microlensing. The characteristics say it is a symmetric. I mean, how you identify the microlensing event. So we see the light curve. I mean, if had a symmetry around the peak, it could be a microlensing. And then it is an achromatic phenomenon, because basically this microlensing, when the light from the background source is deflected by the foreground object, which is dense object. So light is deflected. So this light is deflected and we see the amplification of the background source. So it has nothing to do with the color of the star, color of the source. So it is achromatic. So you need at least 2 end observation, minimum 2, so that you can check the achromatic phenomena, whether it is the similar behavior in 2 different bands. If you have multiple bands, then it's even better. And it is a unique event. So even you find a microlensing event, so you have to make it sure that it is not repetitive. You don't see in the next year of observation. So at least 3 years of observation are required to check the uniqueness of the microlensing event. So that is the constraint. Now, as I said, first year in 1998, when we started this program, we have 6 by 6, 1K by 1K CCD having the 6 by 6 arcnet field of view. But when we started in 1999, we have the 13 by 13, 4 times larger field of view. But then we are again started from 0. I mean, when you start program in 1999, again, we needed minimum 3 years of observations to check your microlensing thing, all that field of view, 13 by 13 arcnet field. So for us, it has become a 4-year job, not just a 3-year job. And limitation is that you need 3 years of observation before you analyze, you say that, okay, it is microlensing event or it is not a microlensing event. So you have to wait for all this data. Just after 1 year or few nights, you cannot say that it is microlensing or not microlensing. So you need to wait. So that is the limitation why this program is not continuing from different telescopes. So we started, as I said, so CCD used, 2 CCD used this central coordinate given by our French group. So because they were also monitoring, of course, our field of view is still, I mean, 13 by 13 is very small in comparison to what they were observing with the 2.5 meter INT, but we have started this target field and we were using this R and I band observation. So, and we observed 141 successful nights. But when I say this 141 successful nights during 4 years of survey, actually we tried for almost 280 or 300 nights. What happened? That you needed a deep observation, really deep observation with 1 meter telescope. And it was thought that at least we need 1 hour of observation in one single filter. So 1 hour in R and 1 hour in I. So like in today, if you take the 5-minute exposure, on 12 frames, you need then there is a readout time and you need extra time. To save that time, we plan to observe this with a 20-minute exposure time. And then to have this 20-minute exposure time, you needed an auto guider working condition. So unlike today's era, when you need, 4 or 5 minutes, when you go to 1.3 meter telescope and it takes just 5 minutes to fix the auto guider. That time, it was hell. It took a lot of time to fix that star in the auto guider. And then auto guider should work for all the 20 minutes, at least to get 1 frame. sometimes it happened also that during that 20-minute frames, the star left to the autoguider, and then you see the trailing, and that whole frame is gone. So you needed this autoguider working for your full 2-hour observation to get the quality data. So that was one limitation. It had happened many times that, okay, our autoguider didn't work and we lost a night despite having a good night. Sky was clear. One limitation was this. And then when we had this 2K SSD 20-minute exposure, even many times our computer crashed. It could not store that kind of image. Now, because we are talking about 4.4 into about 6 pixels. So it could not store the, many times this computer simply hanged. So we have to reboot it, but that frame is gone. So these were the limitations at that time. So I was there on one monitor telescope whenever CCD detector was there. So during the observation season, which start from for Nainital, we start from the late September to early October up to the mid of January. So that is a season for M30 galaxy when we can see from north the hemisphere, and because we needed 2-hour observation every day. So we have started this in 1998, and there are 34 nights, 37 nights, 35 nights, 35. There are successful nights we have taken under this survey, Meinel survey program, and total it was 141 nights. So this is the small field of view, 1K by 1K, and then we have the larger field of view. As you can see that there are not many bright stars. Most of these are actually foreground stars or galaxy stars. Of course, few of them are M31 galaxy star, but to have this kind of brightness for M31, you needed something like -7 or -8 brightness for those stars. They should be really very bright object. So now the optical depth, what we call the chance of detecting one microlensing event among millions of stars is just 1. So it is very, very small optical depth. So you needed to observe millions of stars in this field to check your microlensing thing. So that's why we have given deep exposure 20 minutes, then we combined all of them to make it 1-hour exposure in R band, and 1 hour I actually wanted, but most of the time it was 40 minutes only. But this was the case. So in that way, we could detect stars down to something like 21, 22 magnitude in 1-hour observation. But as I said, we needed even fainter one. We needed those tiny flux which we cannot see as a star. So a different technique was used. This normal photometric technique, which we normally do for the star photometry, will not work here. We can have only few tens of thousands stars at most, or even few thousands of stars. But we are talking about we needed millions of the light curve to find one microlensing event. So a new technique was developed at that time. That was pixel method. Pixel analysis. Each and every pixel you have to analyze. So there were various things when I'm not going too detail in the scientific part, but what happens when you have the pixel, and if you put all those pixel flux at the same level, and if some flux of the pixel is amplified, and you are monitoring that pixel over a long period of time, then you can see that amplification in that particular pixel, and you can say, okay, here is some star is amplified, and it could be the microlensing event. And then you test other things like uniqueness, achromaticity, and symmetricity. So our job was to detect this data, and it should be well above your detection limit, 3 sigma level. So cutting short, we have detected first microlensing event from India, and this event was recorded in our 2K by 2K CCD, not in our 1K by 1K CCD. So just for later 3 years, we could detect this, but the first year is from the MDM telescope, 1.2 meter MDM telescope in Cape Arizona. So we have taken data from that telescope, and we supplemented our data with the MDM, and you can see the first one is from MDM, the latest are ours. So you can see a very good, nice light curve, and that is consistent in R and I band. Of course, we have a little bit error because it is really faint source. As you can see here, in the left side, there is no source. There outside, on the right hand side, you can see our first microlensing events. So we check this light curve for all the characteristics of microlensing event, and we found it. We confirmed it as a first microlensing event, and paper was published A&A that time. and we determine various parameters, and then we characterize it, and we found that, okay, this star is reaching up to this stage, almost minus 5.5, something minus 5.12. In our band, we have determined the color, and we found that, okay, this could be a 0.5 solar mass star lens. The lensing phenomena has happened with a source which is 0.5 solar mass, and that lens could be either in the halo of our galaxy or in the halo of M13 galaxy. So we detected this. Apart from the microlensing event, we detected, now we have the data. So this is one thing that we have detected the microlensing event, but we have acquired 4 years of data of 6x6 arcnet field and 3 years of data of 13x13 arcnet field. So we started mining that data, and we detect many interesting things like CFIT variable, for example. So we have detected many CFIT variable. In this paper, we have reported 26 variable, CFIT variable, which we detected through the photometric technique, normal photometric technique, which we often use for the resolve stars, and we determined the distance of M13 galaxy using these CFIT variables, and reported the distance of M13 galaxy. At that time, the Hubble program was also going on to detect the precise distance of M13 galaxy, and their value was some 780 kiloparsec. Of course, our array is 45 kiloparsec. There is something like 20 or 25. So, but our value was very close to the value given. So then later we again started searching here. We again started searching for the field, but this time searching the CFIT using the pixel analysis technique, the same through which we have detected the microlensing event, and we detected many more 39 low period CFITs. So we have gone down to something like 4.6 days period. So 4.6 to 14 days period using the pixel analysis technique. As you can see here, we published this paper in again A&A 2010. So then we have detected novae in our field also, as we are monitoring continuously our field of view, same field of view over a long period of time. So we are checking various stars, and we found that, okay, there was 2 M31 novae, as you can see the light curve, and we determined various parameters and decayed all these things, and we published these papers again in A&A. Then in mining that data, we found the W microlensing binary stars. We characterized these W binary stars, and recently we have published this paper in Research in Astrophysics and characterized all this existing binary stuff. And then very recently, we have found this light curve also for 4 years, as you can see here. So top 1, 2, 3 up to this dark patchy line close to 3,400. That is the Nainital-Cape Survey data. But we have started this program on 2 meter SCT also. So we have some data from the SCT, and we checked that data, and we found that there is a secondary bump in the light curve. So this was a very bright star, as you can see, 15.8 magnitude bright star of M13 galaxy. So it was actually a luminous blue variable, AF and what we call Hubble Sandwich variable. So using the Nainital data as well as SCT data, we characterize it and determine various parameters, and we found that, as you can see, the right hand side color variation is there, corresponding to right hand side you see the temperature. So temperature is varying something like from 8,000 degree Kelvin to 33,000 degree Kelvin for this star. So, and then using the SFOS 2 meter telescope, we did the spectroscopy of these objects. We have plotted SED, and we found the infrared access, and all this work was published in Astronomical Journal recently. So though we have stopped the program, microlensing survey program long back, but we have access of the data, and we publish a variety of sources using the same data. Microlensing survey. So now we have stopped this program, but it is not just we at Aries. We have started this program in SCT also. Anupurna, in fact, took lead to continue this program using the 2 meter telescope. But this kind of program need a dedicated telescope time, and it's very difficult today, when there are so many students, requiring time, observing time on these big facilities, and we have limited telescopes. And so even she started this project, Stalin was involved in one of the projects, lensing project, using the 2 meter S2, but no one could continue this project for a long period of time because of this limitation, because we needed a dedicated time over a long period of time. So this is the one problem we faced here. So in future anyway, now we are going to have this 4 meter LMT, and where it is going to observe our zenith sky, half degree width, and then whole sky patch over a long period of time, and it means we can monitor these sources over and over again throughout the cycle or over a period of LMT period, and this type of program can be taken up from there. I mean, and can check for the microlensing thing, and of course then can determine the various parameter or constraint on the dark matter, all this thing. So of course this program is also going on 3.6 meter mic. It's not microlensing but lensing program, and led by Gian Surdej lensing program. But again, the same limitations. Unless until you have a lot of data, you cannot get the paper. So this is that is a limitations with this kind of surveys. So even these kind of survey are run in automatic telescope form and various by big groups where they have dedicated telescopes or dedicated telescope time, and not as an individual or small facility. So I think summary of the survey that okay, we have done all these things, and we detect one microlensing candidate. We have detected 350 variable stars. We reported 350 variable stars, including 55 CPs, no way, W star, luminous value, very, and we have published 8 different paper in the microlensing from the microlensing survey data, and surveys was quite successful despite many limitations and smaller group. Yeah, thank you very much.
Good comments.
Since you have such a definitely huge body of data, despite all limitations, my question is, did you come across any variable star which is of a new kind, previously known?
See, actually what happened whenever we search these kind of peculiar stars, like for luminous blue variable, when we saw that okay, this is peaking, and in 4 years time it was just this base level, even not gone beyond that. It was a peculiar for us. I mean, then we searched for literature and then found that okay, this is the first by LBV reported by the Hubble and Stanton, actually. That is called Hubble and Stanton. We were back in 1955.
There are few in number.
Yeah. So yeah, there are in Andromeda Galaxy there are only four LBVs.
There are total, there are 10.
Yeah, in total in galaxy and nearby galaxy. In M13 galaxy there are 4. So we were not aware of any such LBV at that time, but when we were mining the data and we found that peculiar light curve, and then we started working on that and searched literature and found that okay, this is one of the first LBVs reported. And then of course with data completed data from the SCT and some other data from Penstar, we work on the this data and publish the paper in 2019. So yeah.
I have one question. How long these microlensing events typically last?
It is unique event. It has one time. See what happens actually. Duration. Yeah, duration actually. Okay, so duration is like few tens of days to even can be like 100 of days or something like that. It depends on what is the source size. I mean, so it can be go very fast. So if it position, because what is happening, you have the foreground and you have the background, right? So it is basically movement. So if your foreground fixed and background source is going on, so how fast it is going, you will have that duration, right? So it is normally the microlensing event detected by other groups, and if you come, see our microlensing survey also, we can say that okay, it is like 10 of days to almost 100 days of.
So, if I'm not wrong, then microlensing events are also used to detect transiting exoplanets.
Yes, the program is going on in fact. So by US group, I mean they are searching for the exoplanet. What happens actually is very simple. So you have the microlensing event, and now in the foreground you have a planet also. So what will happen? It will go up and down, and then suddenly you have one more planet, right? So it will again go up. So what happens? You have a rising curve and falling, and suddenly one peak more, one extra peak, very small peak. typical duration of that peak is like 1 or 2 days. So it means that you need a fast observation, because within that 1 day, you have to have full light cover of that peak, small peak, due to the planet, right? So if you have a dedicated telescope and fast sampling, you can detect it. So like Ogle has done this. So they have already reported exoplanet detection using the magnetic detection. But again, in the exoplanet detection, it is not very common. So there are very few planets detected. I think it's single digit number detected by this telescope.
I had one last question.
No, that's it. We can discuss it. Sure. Dipankar.
Yeah, the comments of Pranchu is our first batch of the intake PhD student. We have to motivate him and he's going to look at the ILNT data.
Okay.
So I think what he was also trying to understand what is the limitation of your exposure time, because ILNT has a fixed exposure time and so on. So what I understand, you need continuous data almost. So how many hours in a night you need?
See, it depends. Why we did it 2
No,
hours?
I mean, you have to be modest.
Yeah.
So if you are given, of course, ILNT data is unique. Now I'm also here. If you get a 1 meter class in Devastal, how many hours you need in a night?
I think
to have this campaign.
If you want to go up to same deep level, I mean 22 magnitude or 23 magnitude, it is like 1 hour in one filter. So we need at least 2 filter. So we 2 hours.
3 hours.
Including the overhead.
So I think you got my question. So we'll keep it in mind.
Yeah, actually, which require we have separate discussion, how we can couple 1.3 meter, and we can have.
You can get a 1 meter new telescope.
No, other thing I can tell you, there, because of better seeing, whatever you could detect,
It is faster.
easily 2 magnitude fainter you will get. Because this is observationally proven with 1.3 meter and 3.6 meter, you remove the aperture effect, right? Light gathering power. Even then, this has been quantified that at least couple of magnitude fainter you are observing from Devastal. Two reasons, seeing plus dark sky.
So what advantage we will have because of this? Now we can go deeper and deeper. So we'll have more number of stars. So here this optical, as I said, one in a million. So if you have more number of stars, then you will have more chances to get the microwave. The number will increase.
Let's stop here. So thanks, Yogesh.
And that's why I told you, Yogesh could complete his PhD.
Ramtha was very scared actually.
You have very questions. No, I was scared.
Next speaker, Professor Pandey, speak on surface photometry of galaxies using Sampurnanand.
Odd man out in this system.
Not at all. Not at all.
Okay.
Yeah. So if you'd like to use this.
Yes, I can do that.
Like some.
Yes. I'll talk about surface photometry of galaxies, which we carried out using 1 meter telescope here, as well as other medium-sized telescopes at VVT and later on at HCT also. But the beginning was very interesting. Interesting in that several senses. First is a 1954 born person joining observational astronomy and trying to do something for galaxy photometry. But thanks to Ajit, who had belief in me, because he had known me from TIFR days, I was working with Chitre in solar physics and doing nothing for almost 10 years. So after the establishment of ICA, he invited 2 of us, myself and Dr. Chakravarti, who is no more in this world. And he asked us to read some books on CCD photometry, low light level detectors, and things like that, and invited us to join this polarimeter observation program. And before we went back to Raipur after staying about a fortnight, I don't remember now, he gave me a long list of objects I think it's a CFA redshift survey. All kinds of galaxies were listed. And then we had an observing time at the 1 minute telescope. Vijay Mohan was there. So he actually trained me how to do observations at Nainital and Ajit Kambhavi at Ayuka. And that is how the observation program on surface photometry began. And the first night that I had, I still remember, I don't know whether Professor Ramsagar was during my first night, or not first night, during that period. I don't know if it was 1990 or 91, but during the Pauli period. So interestingly, I don't know, we picked up spiral galaxies. And they're very complicated ones, as you can see. Unfortunately, I don't have the original pictures taken with this telescope because we could not work it out further. But we used this telescope for training ourselves. That time, you can remember, the IRAF was just installed on one of the sun workstations at Ayuka. And we were among the first users. Ujha is there. He used to travel from Nainital to Ayuka. I used to come from Raipur. We used to spend several months together. Learning IRAF, that also was not an easy task. But fortunately, the manuals are available. So we literally followed the manuals, how to move ahead and how to analyze. So this 3 galaxies served as a trainer. It's complicated ones, fitting ellipses, you can imagine. But this actually taught us how ellipse would go on if the isophones are not truly ellipses and you're trying to fit ellipses, what will happen? How, if you try to draw a light curve, how the light would look like with galaxies like this, very complicated structures. So these 3 galaxies, I think we observed on the first night. And we could not carry it forward. Only thing we did was we presented some papers based on this galaxies at the ASI meetings. The first one is the DVRI imaging on the very distant spiral galaxies, NGC 2701, and for all 3 galaxies. Brightness profiles. Another thing which I use them to learn is how really one does the extinction correction for the galaxy as a whole. So I had little bit knowledge about doing for the stars. For galaxy, doing galaxy extinction correction, then calibration using the Tyndall star. So all these things we used this spiral galaxies, and Vijay Mohan was there all the time. He also used to make visit to Ayuka, and I think it took us several visits to complete the whole affair, starting with data reduction, and that was a huge task in those days, right? We used to spend hours together discussing at Ajit's house, sometimes from lunch up to dinner in his house. And same thing happened here also. See, in those good old days, there was some accommodation, there was no place to eat. So I used to have all my 3 meals at Vijay Mohan's house. So after having done something physically, then I told Ajit, see, Ajit, these are very complicated galaxies. It's better to switch to some smoother ones. So I said, let us pick up some ellipticals and lenticulars with very smooth brightness profiles, because I have been reading through the literature. Meanwhile, we submitted a proposal to DST, for which again Ajit literally pushed me. That was sanctioned with 2 research positions. Devendra Sahu and Niharika Thakur both joined. Niharika Thakur left afterwards, but Devendra Sahu continued. he actually, at some times, he felt like leaving the project with great difficulty. I could retain him, but before he submitted his thesis, he was working as a provisionary officer in State Bank of India and simultaneously working for his PhD. This is a very interesting affair. So that is how we continued our observation program on early type galaxies, ellipticals and ASOs with Devendra Sahu after Niharika left. And he completed his thesis, which is in 1999, photometric studies of some early type galaxies, randomly chosen some, whatever you could observe on those days. Devendra Sahu later on, T.P. Prabhu was his thesis examiner, right? So he came for YOC exam. Devendra Sahu told me he wants to leave that job, provisionary officer. He wants to come back to academics.
I was another
So I told him to talk to Dr. Prabhu. So he was selected at IA, and now he's a full professor. So that is compliment when you look back what we did without, you can think of working in universities. So that is one thing. And Devendra Sahu, he had 3 observing runs with 1-meter telescope. October 1992, I think it's again during Deepavali time. November, 6 galaxies, 14 galaxies, ellipticals and ASOs. He observed from 1-meter telescope, which became part of his thesis. Right? And this is the observing log which I took from his thesis only. It's not clearly has come out, but what you notice here is, see, when we first observe very small format CCD, 384 by 5.
Yes.
Other day asked that is no longer there. No. It not even exists now. So, and then by the second and third then, he had 1K by 1K. But again, there were some problems, again came back to 384 by 576 thing. And since these galaxies were nearby, so we used 2 by 2 binning also, just to save time and improve the in exposure times. So, and then, as I told you, the main objective was to carry out detailed surface photometric analysis of galaxies. And then as we moved ahead, we realized that this, when we are working with the smooth galaxies, let us try to find out, because CCD has an advantage, right? Whether this apparently looking smooth galaxies, whether they have some faint structure embedded in them. And as I'll show you, we did find some galaxies who have either dust or cells or ripples, faint disk also, right? So see, this is we kept on improving our objectives as we moved ahead. And this is one sample, complete thing. Those who are a bit aware of how ellipse fitting is done in ILAP, this is Fourier expansion. I0, I is equal to I0 plus A1 sine phi plus like that, 4 coefficients. So, sorry. You see, this for the first paper that we had, NGC 7562. V magnitude, so it's very smooth because elliptical. Electricity, slight variation, but not much. Position angle. Then P4 coefficient, slight positive, disky, look like disky. And these are the color profile on both B minus R and R minus I. Didn't found much interesting. So we looked it back. We examined higher order coefficients also, color profiles with great detail. And finally, it turns out this one. Yeah, I should put all shape analysis just to look for what are the faint structure embedded in them. We made a small presentation at one of the SI meetings and published a paper on NGC 7562. I don't think you can read out, but this is the paper on the single galaxy, NGC 7562. The title was Nuclear Dust in Outer Cells in NGC 7562. And look at this. These are the cells or ripples. And in order to detect this fanned structures, which was not apparent in the single band or even color images, we made use of a clipping algorithm which was available as a part of that elastogram of IRA. Right. So, and what it does is you clip the top 40% bright pixels, carry out the list fitting procedure, generate a smooth model, and one without clipping. When you subtract this, whatever has been removed appears, and that is how we could detect the cells. Right. So B4 could be seen, even though it turns out to be positive slightly here. So this is without clipping. You see positive B4. There is no dust. But when you do the clipping, we do see those what we call as cells or ripples along major axis. But with this B4 coefficient has almost come down to 0 within an advance. So that is the beauty of that technique, which we utilize for looking at the structures in other galaxies as well. Yes, in the same galaxy, we could also locate that there is in the B minus R color image, this graph also is shown here, and in the color image also, it's a dark region, which is clearly distinct. And as outside, you are seeing the domain also. Right, seeing width. So that is how we reported this, and it got published in 1996 in ANA. Another galaxy that he took was NGC 2076, which has clearly well-known dust lane running across the major axis. And he carried out the detailed analysis of the dust features, which was then taken over by another student of mine, Patil. But surface photometry of entire set of some 30 plus galaxies, we did submit it to publication, but before the comments came, Devan Saud has moved to IA, so that remained unpublished. It is part of this thesis only. So that is a story about one student. Then the Patil joined me. There's another interesting story. I was there at Nanded for a brief spell of time, August 1996 to February 1998. So he was a net qualified person, Patil. He wanted to join me for his research. I said, I'm going back to my place. Why do you want to join me? But he said he wanted to do research in astronomy. Okay. He joined, but he worked very patiently, very dedicatedly, and he had made use of the 1 meter telescope also for observing. Right? Only thing is, we started having the same objective, but we focus on, let us pick up the dusty galaxies and try to analyze their properties. So that is how he could finish his thesis. This was entitled Multi-Wavelength Study of Dust Properties in Early Type Galaxies in the year 2003-04. He is now a professor in Patil and is continuing his research work. That is the beauty. It is not that dead PhD. Those who don't do anything, I call them dead PhD. You are the active PhD. Right? So this is, I have picked up only the relevant part from his whatever he had sent me. So he had two cycles of observation, December 1998 and December 1999. And if you look at the observing log, so he had used, by the time he came in, I think it's already 1K by 1K. Next time, 2K by 2K. See how things have moved, technology. So these are all technology-driven research, so to say. So let's start from VPO and Hanley. So what he did was to set a set of galaxies, and out of this 30 plus 11 galaxies were observed from Nainital. They're all known dust. Only thing is we could carry out the detailed dust analysis of these galaxies, and 11 ellipticals and 15 SOs. See, these are little kept. It's clearly known, even in single B-band image, you could see there are dust laying of various morphological types. Right, some are along the major axis, some are the arc sept, some are along minor axis, like that. Look at the color images. And then in order to analyze the dust, right, see, normally those who work in Milky Way galaxy, they know there is a what we call as canonical value for the AV upon EV minus 3.1. But the way they analyze the dust property was different because the stars were resolved. And we are talking about galaxies where the stars are not resolved. So what do? We do a simple method, again using the IRAF. You mask those just occupied regions, right? And create first the smooth model. So this is the B-band image of one of the galaxy, SE 907, something like that. This one, where you can clearly see the dust features. There are two of them. And this is the dust pre-model to large extent. You have to do iteration several times until you reproduce the same thing. But you have to make sure that the dust thing matches with what you see in the color images. So by doing this, you create the dust pre-model. And then for all these galaxies, we did the similar thing. And using the standard thing, which we all know, familiar with, how to create the extinction maps, right? The logarithm of the observed original image, you divide by the model image, take logarithm in magnitude scale. That is how you do. And what you get finally are these extinction curves, right? Okay, so more or less I'm through. There's about 30 galaxies for which this very often referred paper in which was published in 2007 in ANA. Right. So they're all local galaxies in a local universe. Important thing to notice is extinction curves of all these galaxies run parallel to the galactic extinction curve, but they do not overlap with the extinction curve of the galaxy or Milky Way. Some are above, some are below. But one thing is clear, the properties are similar. Only thing is when you say they are lying above the galactic extinction curve, their relative grain size is slightly more than those in Milky Way. When it is below, other way around. So, and then we computed, this is the RV value, turns out to be in the range 2 to 3.5. And dust, when you compute it, this puts a lower limit on the, because there's optical method. If the dust is distributed uniformly, they won't be revealed in the color map or this kind of the way we have produced the extinction maps. But when you compare the optically computed dust masses, which runs in this range 10 to the power 4 to the power 6 solar mass, whereas this for these galaxies, when you compute the dust masses, see, for the young people, if you recall, the dust not only dims the light, it also reddens the light. That's how you can produce the reddening curve or extinction curve, right? And the same dust re-emits at far infrared. So when you look at the IRAS, the far infrared emission, right, you can use them to determine the dust masses and compare with the optically computed thing. It turns out to be at least one order of magnitude than what you determine from the optical things. And see, the particle did one more interesting thing, moving ahead. He looked at the X-rays, X-ray images of this elliptical, because ellipticals turn out to be X-ray bright. And if you look at this diagram, this on the sheet, you have the mass of dust normalized to blue luminosity, and this is mass of X-ray normalized to blue luminosity. So it turns out that those who are brighter in X-ray turn out to harbor less dust, which is obvious because X-ray will do the sputtering, will reduce the grain size. So this is very interesting thing. And he has done some other analysis, which I don't have time to except to show this. On the left, on this side, this is the B-band extinction map. This is the H-alpha, and this is the corresponding X-ray image. So more or less, it's not exactly the matching of what you see for the dust or H-alpha ionized, I guess, or very hot gas. But there is some similarity the way they appear as we see from here, right? So this is an interesting thing that what has given rise to multi-phase IEC. You have cold gas, you have dust, you have warm gas and hot gas existing more or less. There is a spatial correlation, right? We have not done any quantitative analysis so far, but this is very interesting itself to qualitatively examine and suggest that based on X-rays, optical, and infrared, H-alpha, that the features seem to occupy the same spatial region. That is what we call as multi-phase ISM. That is what, same thing again in different galaxies. Right, yeah, multi-phase ISM. And this is the paper which I was referring to, Patil, Pandey, Kimbhavi, and Devanasa, 2007. Right. That's all. Thank you very much.
Very quick comments.
In the RV estimation that you did for the galaxies, that would work, but how do you take care of the galactic contribution of extinctions?
That we have not, that is, we have not taken into account. You're talking about galactic expansion.
Yeah, on the galaxy.
On the line upside. That we have not taken care of. Because no one does that kind of thing. When you look at the extinctions and yeah, only thing you have to take care of, you have to choose the galaxies. We are above the galactic. Yes.
You estimated mass based on iris, which is 8 times or
roughly 1 order of magnitude.
The region for this.
That is because, see, whatever we estimate from the optical extinction curve, that looks a lower limit. You don't know any information how the dust is distributed across the galaxy, right? For example, if the dust is distributed throughout the galaxy, it won't be seen in optical images, color index images, or extinction maps. But IRAS sees it infrared, 60 micron, 60 by 100 micron. Yeah.
It lost.
So for ISM, what is the source of H-alpha?
Oh, that's an interesting question. But we don't have clear-cut answer. But presumably, see, if you have in a galaxy an environment where you have dust grains, X-ray also present, so this does perhaps act as an agent to transfer radiation from hot region to the cool gas, which gets warm up, and that is a way you can explain that there is a X-ray, and the very fact that higher X-ray, bright, the galaxies will bright in X-rays have less amount of dust. So there are several models available. I don't have time to talk to, what is called the evaporation model. Right. So this seems to fit. Dust is acting as an agent. Transfer heat from X-rays to, that is how you can get ionized gas.
Okay, let's thank our correspondent.
Thank you so much.
We have the last speaker, Alex Pancha, about aspects of short period extreme values, period variation of short period extreme. You need something? So that we can use this.
Okay.
And
Hello everyone. Title of my talk is Studying Period Variation Contact Binaries. We observed these contact binaries using 104 centimeter Sampurnanand telescope and 1.3 meter fast optical telescope. This work is part of some other main work under which we characterize these contact binaries using photometric data, as well as we do some spectroscopic analysis using low resolution Lamos data also. So in this talk, I will be discussing only that period variation part in which we have used that Sampurnanand data, telescope data. So contact binaries, you can see in that image, is a class of eclipsing binaries. These systems, in these systems, both the component have spectral type late F to K, and both the systems share a common envelope. You can see in this figure, around that dashed line, you can see overflow of material, that is inner Lagrangian point. So both the component can transfer material through this component. And due to that common envelope, both the components have almost similar temperature, and most of the system observed till now, in all these systems, the temperature difference is found less than few hundred kelvins. Due to a small separation between both the components, the period is also very small, and their period is normally less than 1 day. This is a typical light curve for some random contact binary observed in Kepler mission. And you can see continuous change in variation of flux in this light curve. The y-axis is normalized flux, it's not visible. And due to continuously change in the cross-section area which we are viewing, we will see continuously change in the flux of this kind of system. We can get different information from contact binaries. Due to their closeness, we can get idea about how do both the component interact with each other. And most of the systems show asymmetric light curves, so they show some magnetic activity or spot formation. So doing some extra work like high resolution spectroscopy and other things, we can get information about their surface features. As mentioned, shown in previous figure, because of their closeness, most of the contact binaries also seen same for other surveys. The fraction is actually less in Kepler and TESS because they mainly target bright stars because they are dedicated for exoplanet detection. So this is the idea of period analysis. You observe a system. Around primary or secondary minima. You have light curve, and around that minimum brightness region, you fit a parabola, and you get observed time of minima. At the same time, you have a period of the system from that photometric data, and on the basis of that period, you can calculate the expected time of minima, and you find the difference both these minima, and for one orbital cycle, then next orbital cycle, and then so on. So you see how do these difference varies with time or with orbital cycle. So this is light curve for some contact binary star. The shaded region here is primary minima for this star. The continuous line is fitted parabola, and the lowest point in the fitted parabola is the observed time of minima. And using that equation, if you have period of the system, you can calculate the expected time of minima for that specific period for that system at that specific orbital cycle. Apart from using default and ST data, we also search these sources in other photometric surveys also. We have different surveys like SuperVAST, PTF, and JTF, and in all these surveys. Idea is we are trying to investigate the period variation over a long period. So using data from other surveys, we can expand that time span of the observed data. Like SuperVAST data, we can get some point around 2002 or 2004, and from CRTS and other surveys, we can get almost 20 years of data. And other thing is that TESS and Kepler photometry is more precise, and they have low cadence. So if you are especially targeting short period variation like UMA binaries, so it's very good to use their data also. So our period analysis will result that OC variation with the orbital period number, and we can see different shape of OC diagram. For linear shape, we say that constant, the period of the contact binary is constant. In case of parabolic variation, this normally happens due to mass transfer among component of the contact binaries. If you have third body around that contact binary system, it will show some effect on time of minima at regular interval, and you will see some kind of cyclic variation in the observed OC diagram for the system. If your system has eccentric orbit and little bit deformed, then primary and secondary time of minima follow a different pattern, which I will show in some next slide. For our sample of these contact binaries or WMA binaries, we selected sample from Catalina surveys. There are thousands of UMA binaries reported in that surveys, as I mentioned in previous slide also. So we applied different cuts because we wanted to observe one candidate at each night at least. So we selected all the candidates with period less than 0.3 days, and all the bright candidates were already studied. So we removed all the candidates with magnitude brighter than 12. At the same time, we are utilizing moon nights, moon phase nights. So during that night, moon brightness is high, so we don't want to go to that faint limit. So also removed candidates with magnitude greater than 14. And then amplitude cut, which was used to remove all the ellipsoidal variable from our sample. And then for visibility, we selected some declination range. And as I mentioned, this is part of some another work. In that work, we are also using some LAMOS data. So we cross-checked these contact binaries in LAMOS archive also. So after that, we found almost 100 contact binaries, which were not studied in previous study and follow all this criteria. And we are continuously observing these variables, and some I am showing result for some of the variables. These are some variable, 9 variables, contact binaries. For some systems, we found there is no change in period, and OC diagram shows a linear variation. Different symbol or different color represent different data sets. Like for some time of minima are determined using SuperVAST data, some CRTS, some default, and some default, and Sampurnanand as well. For some contact binaries, we got some parabolic variation, which is normally due to mass transfer among their components. Similarly, for these 3 candidates. This is another system which we are studying. This is a semi-detached system. This is observed in 4 different sectors by TESS. You can see concentrated points after 0th cycle, orbital cycle. And before that, we collected that data from other studies, previously studies. The scattering is very high in previously observed data, but still we managed to fit parabola, which is an indication of mass transfer. But if we see only that test part of OC diagram, we see that primary and secondary minima are well separated and follow same trend, and but they are separated by some amount. So the upper panel is we have fitted some cyclic function to determine parameter of presence of some third body. and lower is variation is due to its eccentricity. So this system is eccentric system, and it is normally expected that there is some another body orbiting this system at a period of around 150 days with in a very wide and eccentric orbit. The orbit eccentricity for the third body is found 0.7. But this system is still under observation. We are collecting data for this system. So in our analysis in those 9 systems, apart from that last system, we found 2 kinds of variation: linear variation, which is normally represented by this line equation, and parabolic variation. In linear variation, we don't have to do much because system is not period is not changing with time. But in case of parabolic variation, the curvature of the equation, the C part, can give you idea about rate of change of period. And using that equation, we calculated the rate of change of period. So these are some of the equations I will quickly show for these systems. And you can get more information from the photometric data using different eclipsing binary models. You can get masses of individual component, radii, and luminosity. If you have photometric data alone, then these parameters will not be accurate, but you can get good accuracy if your system is total eclipsing binaries.
Also orbital parameters.
Yes, yes. And in our analysis, we use Phoebe and drive some of these parameters. And these are conclusion of my talk. We studied these 9 systems using Sampurnanand and fast optical telescope. We found that 5 of the system have constant period. And point should be noted that we are using that data duration of 15 years. So on behalf of that data, we are concluding that their period is same over that constant. If we want to detect some long period changes in data, then definitely we need to observe this system for more time. And apart from these 5 systems, there are 4 systems for which we detected some period change. And using results from our photometric data analysis using Phoebe, we converted these period change into mass change rate. And we found that the primary mass of the system is changing with respect to time for this system, and from which component to which component mass is transferred. So the sample was for almost 100 contact binaries. Rest of most of the contact binaries are still under observation using Sampurnanand and dephotons. Thank you.
Yeah,
So that when I see there is a presence of a third body.
Yeah.
But the both system in this in such binaries or the late type solar type star, they have a magnetic activity too.
Yes, yes.
Or you distinguish that this is not because of the long solar type of cycle?
Actually, we have not like mentioned clearly that this is due to third body, but we are, mentioning this can be up to that period of due to magnetic activity also. We did both the analysis, and we have not published this result, but we did both the analysis, mentioned both the analysis, without any like conclusion.
So my question is that
yeah, so you used the initial survey data from TESS and other space-based observatory and other transients, and then you went for your own observations using Sampurnanand. So I would like to ask that if you have a data set for 15 years for a variable star, and now you are observing it for few nights on a telescope, how would that few more nights aid in your conclusion?
At least in this this analysis, it will not add that much. But the other part is derivation of parameters using model fitting.
I don't know. You can show the previous diagram. The earlier,
Yes, that is more informative.
you just saw the earlier.
But
you just
for-
saw these two blue lines that are changing the curve. It may go up. Previous one. Previous one, we just saw the where one point you had 1 point is there and just showing the you just see that.
Yeah.
Previous we just see the last point.
But all the systems were not observed in TESS and Kepler also. So we are collecting data, but if it is not observed in those systems, then it is definitely adding to their variation. Like you can see in this figure, if we have like super vast data and we are not getting good data in CRTS itself, because cadence is not that good in CRTS, we will have a large gap after that. So we will have to fill that gap with using default and Sampurnanand optical.
You mentioned you used the most low resolution also for some of
Not for this.
What is that for?
Actually, that was for some kind of emission line due to magnetic activity. We compared their data with the inactive star of same spectral type. We subtracted spectra, and we try to find out if there is some field in observation or emission in the line of H-alpha is some that is for this.
You want something? Okay, well, let's come to the end of this session. We thank all the speakers. There is an announcement from Santosh.
Yeah, Brijesh had made one request. You know, Dr. B.N. Ashoka, he did PhD with Professor Ram Sagar, and he had a long association with 1 meter telescope, and he used this telescope for his PhD thesis as well. So he has sent one audio clip, and it will be nice if you allow. We can please play it.
We, the ISRO team, Dr. Sita and myself, under the leadership of Dr. Mara, was involved in collaborative project with the erstwhile UPSO. We wanted to carry on the past photometric observation from UPSO using our 2 or 3 channel photometer on 1 meter telescope. We came to know that Nainital has good sky conditions. Dr. Marar and myself made a visit in 1989 to assess the logistics to set up a collaboration. Dr. Pandey, the director of UPSO, welcomed our visit and assessed our program and assured us a good amount of telescope time. At the same time, he apprised us the limitations in the observatory in terms of available equipments and logistics because it was under UP state government. He also explained us the limitations related to our living conditions in terms of food, transport, and accommodation. He told there is no guest house and canteen, but we will arrange a cook whom you should pay and get him all the raw items. He can prepare food in the place where nighttime coffee is made using a kerosene stove. But we assured that he would make our stay livable. We too promised him that as long as we get good data, all other conditions and limitations are secondary. Then he formed a team from UPSO consisting of Dr. S.K. Gupta, Dr. Chaube, and Dr. Bhatt for the collaborative program with ISRO team. Our first official visit was in 1989. We carried our 2-star photometer. We traveled by a taxi from Delhi to Nainital. We carried with us all the required kitchen items for our cook. We started our first observation on the 1 meter telescope with our photometer. We noticed that the telescope was well maintained. Finding and tracking was good. The sky conditions were photometric. We observed for a week and got good data and gained confidence that it is the right place to continue our collaboration. Then onwards, we started our planned observation with a minimum of 1 visit every year for a stretch of minimum 10 days. In one of our visit, we carried a micro advanced desktop PC from Bangalore to Nainital since there was no PC available in the telescope room. However, with the time, all the observing facilities were made available in the observatory. The next director, Dr. Mehraji was kind enough to get us all possible facilities and continue the support to our group. We continued time series photometric observations of series. We also continued our wet campaigns from Nainital for the asteroseismological studies of pulsating white dwarf stars. Meantime, we modified our 2-channel photometer to a 3-channel photometer, which helped us to get continuous data without breaks. Generally, such continuous data is preferred to avoid areas in the discrete Fourier transform. When UPSO came under DST, due to the immense vision of the next director, Professor Ram Sagar, the logistics improved considerably in the observatory. He was kind enough to allot a good number of nights for our program, in spite of increased demand for observing nights due to many research students. He was kind enough to become my guide for my PhD together with Dr. Sita. The data obtained mainly from UPSO 1-meter telescope and one wet observation involving 1-meter telescope and the CV is the basic data for my thesis. We duplicated and made one more full unit of a 3-star photometer and left it permanently in the observatory since 1998 for our mutual usage. Since Nainital sky conditions was very good and UPSO is in the northern hemisphere, and since we were involved in time series photometric observations, a new requirement came from South African Astronomical Observatory, CAO. Don Kutz and his team proposed a possibility for the study and survey of rope stars from UPSO. He made a pilot visit in 1997 and used our photometer on 1-meter telescope. He could easily detect millimagnitude variations in time series photometric data in real time on the computer screen. He assessed the excellent photometric sky conditions. He declared that this place is fit to establish the collaboration for the survey of rope stars in the northern sky. The rope star survey got the DST approval with the participation of UPSO, Nainital, ISRO, Bangalore, and SAAO. Santosh from UPSO and Girish from ISRO became the first PhD students to work on this program. They successfully completed their PhD using the data from 1-meter telescope. After Kutz, Peter Martinez took the charge of this project from SAAO. Dr. Santosh, after his PhD, you are now continuing this project using fast CCD photometer. He extended his collaboration with a few more countries, including Belgium. Now the institution is renamed as eighties, which is an appropriate name to take. The commissioning of 3.6-meter Devastal telescope is the witness for the remarkable growth and capability of the institution. The effective management and use of 1-meter telescope for 50 years in this best site is the power behind this growth. The Golden Jubilee celebration reminds the history of the 1-meter telescope and the progress of the institution. This event is a motivation for the younger generation. I wish all the best for the celebration. Thank you.
So now I request the director to say few closing remarks.
No, closing.
For today's session.
So I think there's a practical announcement. So those who are staying in the guest house and those who are staying inside also other places, there's some arrangements done. I do not know. For seniors, there are some cars. There is a bus and a minibus. So already I think one trip is already gone. Today, the function is actually in a hotel. It's in the Jolarpeta, which is about a half an hour's drive from here. And we have invited Jubilee. Sorry. We needed a helicopter for that. Yeah, I'm mixed, you know. Born and brought up. So the point is today, actually, all family members of staff members of Aries are invited. So we'll have a large gathering there. But it's a hotel. We'll have some space outside also. So hopefully it will be a pleasant evening. So please do join us. So depending on your age, the appropriate vehicle, please take, because the buses are primarily for youngsters. Because the bus has to be parked actually slightly lower height, because the hotel is at the top and you have to walk a few hundred meters up, but we'll try to get the car all the way up to the top. So please, we will start probably one bus, even the bus ride may be there already, but for the car, it can take about half an hour and we'll start.
So we can start from the guest house.
Guest house, yeah.
Thank you.
Let us say 6:30, he is saying.
6:30, yes.
Yeah,
It is actually,
it is more or less. We gather in office.
Yeah.